Welcome, everybody. Welcome to the Open Science Café. This is an event for Berlin Science Week, and it's organized by the ORION Open Science Project, which is an EU-funded project, and it's a project that is aimed at bringing more open science to researching, performing and funding organizations across Europe. And also the Max Delbruck Center for Molecular Medicine based here in Berlin. So this event is, like everything in the last 8 months, something of an experiment of turning something that was is usually a in-person event into something virtual. So we'll do our best. But we're aiming for a very relaxed, informal format. So imagine that you're in a cafe and you've got a cup of tea or coffee and a cake, and you're just listening to some people tell you some interesting things about open science. If you're here for the whole afternoon, then that's great. Thank you. Settle in, get comfortable. And if you're dropping in for different sessions, then we really hope that you enjoy the ones that you do attend. I'm your host. I'm Emma Harris, and I'll be joined by my co-moderators Zoe Ingram and Louisa Bengtson, who all of us work for the ORION Open Science Project and for the Max Delbruck Center for Molecular Medicine. The speakers are going to be myself in a couple of cases, but also there are going to be speakers from across the world who have graduated, as it were, from our ORION Open Science Train the Trainer course. So these are people who have been learning how to be educators in open science, and they're going to use that knowledge to present to you different aspects of open science. We also have a couple of guest speakers who are going to showcase some in-depth ideas also about open science and the applications that it can have. So I'm going to kick us off in a moment with Open Science, a History, and hopefully that will act as a little bit of an introduction for everyone. If you have any questions, please put them in the live chat, which should just be to your right if you have a YouTube account. And if there's any technical problems that you're having, put them there. I'm not sure if we can fix them, but we can at least be aware of them. Okay. So I will start sharing my screen and we'll start talking about open science, which is what we're here for. So welcome again, and let's begin. Okay, so first talk by me, Emma Harris, Open Science, a Potted History. So this is going to be a talk just a little bit about the origins of open science and how we got to the point where we are now. Full disclosure, it's not comprehensive. It is, as I say, a potted history. It is also, unfortunately, rather Western centric because that's where my knowledge lies. If anyone watching has ideas about or knowledge of open science in other parts of the world, please put some links in the YouTube live chat. We'd love to know more about that. And this is a somewhat idiosyncratic talk. It's kind of what was interesting to me. Okay, so with that in mind, let's just pause to think about what open science actually is. So before the plague, we used to run face-to-face workshops, and we used to ask our participants what their definition of open science was. And so I collected these into a word cloud, and as you can see, accessibility, sharing, public, and reproducibility were important words that came up time and time again. And I think accessibility really is the key word with open science. It's about making science accessible, both in the sense of being able to get hold of data, being able to read publications, but also being able to access in the sense of science being something that everyone can be involved in and everyone can understand. So science communication, citizen science, these kind of topics. And also, I think one word there that I would pick out is fairness. I think open science makes things fairer, and I think that's something that's going to come through in the talks that you're going to hear this afternoon. Okay, so now we kind of have some idea what open science might be. Where did it all begin? Well, let's begin with a science prehistory. So the idea of scientists being competitive, only two T's in that, scientists being competitive started very early. So in the 1600s, for instance, what scientists would do is send their discoveries, but encrypted in a code, to their competitors, to other scientists they were competing with, until they could profit from those discoveries, sometimes through rich patrons, for example. And then they would tell their competitors how to decode these discoveries. So Kepler was sent an anagram by Galileo about his discovery of Saturn, I believe. So the story goes anyway. And he couldn't solve this anagram. And then Galileo sort of revealed to him that he'd made this discovery. So this idea of competitiveness about science is not new. Skipping forward a few hundred years to 1831, the British Science Association was formed, and this was formed to enhance and promote scientific knowledge on a national level, because it was felt that science in the UK, in Britain, was lagging behind, and it was kind of thought of to give a boost. And just in case you thought the problems we have today are new, in 1860, I believe, around then, there was a debate about Darwinism between a scientist, Thomas Huxley, and the Bishop of Bristol. And it was about, whether Darwinism was correct or not. And Thomas Huxley finished this talk by saying that the bishop was willfully blind to science, willfully blind to the facts, was hiding behind religion. And so these problems of fake news and of people putting ideology before critical thinking are certainly not new to us, which is both, I guess, sad and comforting, depending on your point of view. Skipping forward again a little bit to 1971, we have Project Gutenberg, which was the first ever digital library. It was formed in America. So we here have this concept that everyone has a right of access to the collective knowledge of human beings, and that should not be limited to one location, but should be digitally accessible. And then in 1987, there was the first journal, open access journal. Now, I will just add a little proviso here. I believe this is the first one. If somebody knows of an earlier one, and do let us know. But I think it's quite nice that at least one of the very first open access journals was in adult education. And today we're going to hear from people who have been learning more about adult education and are going to be using that to help open up science. So that's got a nice symmetry to it. Okay, so moving on to a bit more modern issues, I think the history of open science and open access can be linked to the history of the internet. So in 1991, CERN introduces the World Wide Web to the public. Also in 1991, physics, the discipline of physics, starts putting their research papers in a repository called arXiv. And this is what we would class as the very first preprint arXiv. Preprint repository. So I think you can see how the internet and sharing research in a more free and direct way, at least among scientists, were very much connected. And if we skip forward 30 years-ish, we can see that unfortunately things haven't progressed as much as perhaps we'd like, both in terms of what the internet can bring us and in terms of opening up science. But we can see again that internet technology, open source and digital technology are being used to enhance the accessibility of science. So in 2011, you have Sci-Hub, which I must of course point out is strictly speaking illegal. It's a bit like the Pirate Bay of academic articles, but nonetheless, that is tied in with our ideas of what the internet might be used for. Then you have the open data button and unpaywall in 2016 and 2017. Both do similar things. If you hit a publication that is not, that is behind a paywall, it will tell you whether it is available anywhere else on the internet, and you click the button, you follow it, and you find that version of the full text article. Open data button does a similar thing when you're looking for data behind an article. So innovations in terms of internet use and open science, as I say, kind of go hand in hand. Then you have declarations and money. So in 2001, you have the Creative Commons was founded, which changes things in terms of copyright and how easily people can share things according to the limitations or lack thereof that they want. And then a couple of years later, you had the Budapest Open Access Initiative and the Berlin Declaration on Open Access in 2002 and 2003, respectively. And I don't think it's a coincidence that these things came together at that time. The Creative Commons, this idea of how can we make things more accessible and shareable, and also this idea that we need to get together and say definitively that things should be open access. And then in terms of funding, you have the Science Driven for Society, SWOFS as it's sometimes referred to, which is an EU funding program that started in 2016, which specifically funded projects such as the ORION initiative and Foster and Fit for RRI and many others, which were specifically aiming to increase the amount of open science, responsible research and innovation, and other initiatives like that in research. So this was not just a declaration or a bottom-up initiative. This was top-down governmental public taxpayer money going towards opening up science. So that's obviously a big leap forward. And finally, I just wanted to talk a little bit about some of the contradictions that we have in terms of who wants to know about science. So the ORION project did a survey of 5,515 respondents, and 66.8% of those expressed a willingness to participate in life sciences research. The reason that those people gave, 88.8% of those people said, was an interest in the research topic. This was a survey that was done across European countries, across 6 European countries, and it was demographically very diverse. So men and women equal, ages were equal. And I think this tells us that people do want to know about science. They do want to be involved in science. And I think that's a really important thing to understand about open science, that the desire to know more about science, the desire to access science is very much out there. On the other hand, 25% of Americans believe in COVID-19 conspiracy theories. And that, going back to the internet issue, if you open the door to people sharing science and making science accessible, you also open that door to people who either through ignorance or malice are sharing unscientific, fake news, pseudoscience, and it then becomes difficult to separate those two things. And you then have a situation where we are overloaded with information, and trying to decide which is reliable or not becomes difficult, and the scientists who are sharing their research get somewhat drowned out in the crowd. But I'll end on a positive note. There are 3,000 active and searchable global citizen science projects just in the project SciStarter, which means there are thousands, if not millions, of people around the world who are interested and engaged in being part of science. And I think when we look at, I said about the issue in the 1830s, that was for a very small number of educated people. And those who got an education were even fewer. So to have moved from a situation when mainly almost entirely male rich people were educated enough to engage in science, so that the point of view of anybody with an internet connection can now be part of science. I think that's genuine progress, and that makes me have some optimism for the future. So I'm open for questions now, and then we'll take a short break.
Hello, it's Marja Pirttivaara here. I would like to ask you, what is your opinion? What is the main driving force for people to be in favor of open science, no matter a scientist or financier or politician, policymaker? What is the main driving force?
That's a great question. Thanks. So I think the main driving force for researchers, and I guess this will be touched on in a lot of presentations, is a frustration with the fact that science is being slowed down by the traditional way of doing things. So data is limited by only being available on a one-to-one basis. Citations are limited by it not being open access. People are misunderstanding science because scientists can't just communicate directly. So I think there's a lot of frustration with those kind of things, and a realization of the system not working as well as it could. I think with institutions, there are maybe more diverse kind of reasons or motivations, ranging from the same kind of frustrations, but also seeing the advantages of open science, of being able to spotlight an institution. And I mean, for instance, we run a podcast, and we did an interview with a gentleman in Canada who works for, and perhaps Zoe will remember the exact name of the institution, but who works for an institution who has made themselves a flagship in open science. So that is their kind of calling card, if you like. That's what makes them special, and they've really aimed to spotlight themselves as an open science, open data institution. And they really stand out, and they found that that's really been very beneficial for their recruitment process, for instance, and their publication record. So yeah, and of course some people simply do it because it's becoming now, with various initiatives, Plan S and European funding and so forth, it's becoming the thing that has to be done. So there's that top-down pressure as well.
Yeah, here is Marja Pirttivaara from Finland.
Yeah, hi, I'm Nathan. I'm a PhD student at Manchester. I work on distributed intelligence and meta-science in general.
Yes, hi, I am Lies. I'm a research data management. I work at the University of Antwerp, and I support doctoral students, professors with their research management. Okay, I think we can start the presentation. First, we would like to ask you, what does citizen science mean to you? You can surf to Mentimeter. We have the link here on the slide. You can type in the code and then send us your answers, and we will go over them shortly. Any more replies? Maybe if some people have a problem logging in, you can always let us know. Okay, some more things are popping up. Okay, interesting. Participation, curiosity, I see. Long life learning, lifelong learning. non-professional participants. What else? Engagement, knowledge sharing. I see, yes, quite a lot of answers. That's okay. Cooperation or collaboration. Very, very good. Okay, I think you know what a citizen science can mean to you. And now we will look further into the concept itself. Yes. It's a scientific research conducted by volunteers and or scientists. It can be in collaboration as well. It's more collaborative to try to achieve a better understanding. It's also for the public to try to gain a better understanding and experience. You don't need an advanced degree to contribute. You can do it in your spare time, really. You can do anything you want if you want to try and teach yourself and try to learn more. It can be about a diverse range of projects with different aims and objectives. It could be about the local community, knowledge of the local environment or community. It could be knowledge gained through experiences. But citizen science can also be done online by online volunteers to submit a large number of data. This is a very brief summary of what citizen science can mean. Okay, next. Yes.
Yes, it's Marja Pirttivaara. I will change now as a speaker. About the value of citizen science, this is also about the motivation, why people are interested in citizen science. It can be personal, like curiosity and altruism. People want to participate, they want to find answers to questions they are interested in. In the previous session, I asked Emma what she thinks what is the driving force for researchers. Now, perhaps you can think what is the driving force for citizen scientists, non-experts. Altruism is perhaps now growing. And then scientific value. It can be verified or direct. It depends on the results, as it depends on science as well, of course. Educational, people are learning to read and understand science and research. When there are all kind of the facts are not always facts anymore. It can be formal learning at the university or informal learning, this kind of lifelong learning project as it is for me. Social, as we saw in this Mentimeter slide, quite a lot of cooperation related words came there. It is bringing society and people closer to science in the sense of ownership, and helps the society and people to address problems and challenges. Challenges in the life, personal life, or the whole life, global life. Policy questions. It is about raising awareness about something interesting people, citizens are interested in. And this can provide evidence-based thinking. Next slide, please. I mentioned I'm a physicist, and that's one reason I want to share with you this kind of finding. Wonderful book, a little book from the 60s. Richard Feynman, one of the Nobelists in physics, he gave lectures about the meaning of it all. Thoughts of a citizen scientist, as he calls himself. He's perhaps one of the greatest teachers in physics. and it is quite funny to read his books. And about questions, what people can ask or should ask, want to ask, and try to find answers. In his book, Richard Feynman says, there is no authority who decides what is a good idea or what is a good question. You can ask questions what comes to your mind. It is actually the same in science, because it is then observations which will show you the road and how to proceed, and sometimes there can be surprises. So it is, we can have this kind of curiosity and creativeness and free thoughts, and even ignorance or misunderstandings whatsoever behind this, that we start to ask questions. But without good questions, you cannot have good answers. And this scientific methodology, I think, as a physicist, one of the most important learnings of getting a training of a researcher in physics was the understanding of reliability of data and text and issues. What is error analysis? You can recognize physicists based on their error analysis. So I hope that citizen science can also adapt the methodology of science, and it should be taught at school, I think. Next slide, please. Oh, yes, then this is for Nathan.
Yes, so I'm going to briefly mention Yuki Happy's levels of participation and engagement. These are kind of a typology that came out of discussions about what's citizen science, what's participatory research, because citizen science is such a broad term. So he proposed these different levels. Each level essentially has more involvement of the citizens within the science project. He very much emphasizes that we shouldn't make any value judgments about the levels, but we should try to move the project to the highest level that is suitable for the specific project, because that will have the best benefits for the community. Within a single project, citizen scientists can be at different levels within the same project. So for example, if we think of Galaxy Zoo, which is probably the biggest physics citizen science project, where essentially people will be shown images of galaxies and told to classify it, I think, either as a blue nebula or a red spiral. I don't know, I'm not an astronomer. And most people will be at level 1 doing that, but a few people notice that there's actually a new kind of galaxy that I think will end up being called green pea galaxies. And so essentially they kind of moved up because they flagged this new problem with the classification task that had been assigned. They engaged with the researchers, and actually they were cited in a number of the papers that were published about these new kinds of galaxies. At the highest levels, we have what's called extreme citizen science, something that happens a lot at UCL. And that's kind of the ultimate level of engagement. Pretty much the problem definition is defined with the community, data collection is defined with the community, and they also participate in analysing it. It's not feasible for most projects. On level 3, we've got participatory science, which is the kind of science that's very common in medical research. And then the first 2 levels are probably what most people think of most citizen science projects. So citizen science is used to address a number of challenges, such as clean water. I've mentioned astronomy, but there's a lot of work in biodiversity, especially around bird watching, which is kind of one of the big early projects. There are also a lot of things here which people might recognize as fitting well with the Millennial Development Goals. And there's a lot being written about how citizen science can contribute to that. However, I would argue that citizen science faces a different kind of challenge. I'll go back to that in a sec. And obstacles. And there's a serious lack of good practices about data sharing in citizen science. There's Groom et al. Who studied a bunch of, who looked at a very large biodiversity observation database and looked at how open and how reusable the data was. And they found that citizen science was systematically the least open kind of data. This is often due to essentially amateur organizations who don't understand how licensing works. And so they end up just having the default license, which isn't as permissive as it could be. So potentially there is a very easy fix for that. Another problem from an open science perspective is that there's a lot of irreproducible results. Osterman and Grinnell looked at volunteer geographical information, which is any kind of citizen science which has a geographical component with the data that's being generated. And they found that not a single study that they looked at could be fully reproduced. Again, mainly due to issues around the hardware and software being used when we're using ads. A third problem is that there's a lack of a consensus on norms around ethical questions. So who owns the data? How open should the data be? And how should we protect citizen scientists? So if we have a citizen scientist who reports 3 invasive species on his app, and someone says, oh, look, there's someone on your app who's reported a species, but they're in my private property, to what extent should we collaborate with that? And there's also a lack of norms around addressing misconduct. Within academia, we have ethics boards, we have a lot of mechanisms in place to make sure that research misconduct is minimized. This is much harder to apply when we have a lot of people who are not academics, they don't have any form of contract, they haven't met strong agreements yet, and in many cases, they might even be completely anonymous. And finally, there's, I'd argue this is the last problem, is less a problem with citizen science than with policymakers, but a lot of policymakers take citizens generated science much less seriously, even when this has been validated. A very good example is if you look at the bottom right corner here, it's a book by Aya Hirata Kimura called Radiation, Brain Mums and Citizen Scientists. And this is a case after Fukushima, where pretty much the only people looking for radiation contamination were the mothers of young children. And the Japanese government very much used that very sexist stereotypes to kind of undermine that research and justify not taking it seriously. There's also a open access article if you don't want to buy the book. But yeah, that's all I have to say for now. If anyone has any questions, that would be great.
It's Marja here. I would like to make a comment about the ownership of data, which you mentioned, Nathan. When I mentioned that I'm very interested in myDNA, and I'm in the myDNA movement as well. And there, the question of ownership of data, it has been discussed quite thoroughly. And instead of ownership, it should be discussed about the control of data, the management of data, who manages, who controls the data. There is even a legal report in Finland prepared by some experts, not citizen scientists, of the Etla Institute, Economic Research. And there in that report, in the abstract, they say, as a general rule, information and data cannot be owned. Information and data may belong to various actors, but they cannot be owned in the legislative sense. Information can, however, be managed. So it would be interesting to hear Lee's comments about that when she is a specialist in data management issues, and she might have a different view for this. I look from this myDNA perspective and some other, perhaps genome data whatsoever. Instead of ownership of data, please speak about access and management of data, control of access. Thank you.
Yes, Lee says, I can't seem to turn on my camera for now, but my opinion about what you say within the University of Antwerp, the regulations say that, well, you cannot take your data home. If you stop working within the University of Antwerp, the data is still property in a way of the university and not of you as a researcher itself. if you leave and you would like to have the data, you can take a copy, but you can never take the original. That's basically the rules in
But
our
what is,
university.
Liis, what is then original data? Perhaps we haven't got any original data when copies, they are as original as everything. So this is in a way
Yes, that's a good
philosophical
question. Yes.
Yeah, so I find with citizen science, it really depends on the project. Those that tend to be led by academics from the start tend to have quite good measures for data management and data ownership and data reuse, and more activist and amateur-led ones tend, not through any bad intentions, to not have these kind of infrastructures or these kind of licensing set up. So there is actually an ongoing project to make it much easier for citizen scientists to just take a very simple license and make sure that their data is reusable. I think it's a big problem, but it's one that we can solve quite easily.
Okay, that was lovely. That was brilliant, guys. I really enjoyed that, and I learned a lot. So I think we're nearly out of time, but I would like to keep talking all afternoon about citizen science, but I also think we have to move on to the other talks.
Okay, hi, my name is Katharina Nimptsch, and I would like to present to you today the citizen science project that we are currently running at MDC. This is within the ORION Open Science Project, and the project is called SMOVE, where SMOVE stands for Science That Makes Me Move. And next slide, please. So about a year ago, there was a new study that was led by the World Health Organization that came to the conclusion that the majority of adolescents worldwide are not sufficiently physically active, and thereby putting their current and future health at risk. And so the first question that comes to us when we look at that headline, we ask ourselves, what does sufficiently physically active mean? Can you click once more, please? So what is recommended by the WHO for adolescents of the age 11 to 17 years old is that they should be physically active 60 minutes per day, and that should be moderate to vigorous physical activity, where moderate physical activity is something like jogging, gardening work, household work, and vigorous physical activity is, for instance, playing soccer, playing handball, or carrying heavy stuff up and down the stairs. And they also say that sedentary behavior, so sitting hours, is a problem, and that should be interrupted as much as possible. So next slide, please. And can you click once more? Yes, thank you. So in Germany a year ago, that had a very wide media echo, along with the stereotypes of the adolescents lying around on the couch and looking at their phones. If you click once more, please. So within this WHO study, they also showed results per country, and for Germany in 2016 the result was that 79.7% of boys and 87.9% of girls were insufficiently active in 2016. So those numbers are quite high and quite impressive. Next slide, please. But even, I mean, this study came out a year ago, but we started actually planning SMOVE before that. And even before that, it was known that physical inactivity and sedentary behavior in adolescents have unfavorable impacts on certain health outcomes, such as chronic disease risks, so higher risk of cardiovascular diseases, metabolic diseases, musculoskeletal diseases, and also later risk of cancer, but also immediate effects on obesity, lower fitness, but also school performance, and social and psychological health indicators, which can be overall well-being and self-esteem, for instance, or how well the students or the adolescents have a social network around them. And it's also clear that sedentary behavior is an independent risk factor of physical activity. So even like after a day of sitting, we cannot compensate fully the negative health effects of sedentary behavior by being physically active in the evening, for instance. And we focus here on adolescents because they really play a key role. Also because an inactive lifestyle during younger ages tends to lead to an inactive lifestyle and the associated disease risk during adulthood. But so far, little is known about the duration and the determinants of sedentary behavior in adolescents. And this was actually also mentioned in this WHO study in the end, that there is not enough knowledge about determinants of sedentary behavior. And also the overall data on physical activity and sedentary behavior is insufficient. And if there is data, it's mainly questionnaire-based, which has certain types of bias, such as potential under or over-reporting. Next slide, please. So the objectives of SMOVE that we had was to assess physical activity and sedentary behavior in adolescents with an objective measurement. That means with accelerometers, which are like small devices that we use to assess physical activity. It's small devices that are measuring the movement in three directions, so in 3 axes, and so we can find out whether the participants are physically active or whether they are sedentary. And we also wanted to identify lifestyle and environmental or other factors that are related to physical activity and sedentary behavior. And here comes the citizen science part of our study. And this we wanted to do based on critical input from the citizens, so from the students in this case. We had a feasibility study before that using established questionnaires. But the important thing here, I think, is really that we ask the students, what do you think is affecting your physical activity or your sitting hours per day? So that makes this project quite unique and quite interesting, I think. And then our third objective was to raise awareness of the importance of an active lifestyle for health among the students. Next slide, please. So SMOVE is designed as a school-based epidemiological study. We want to assess physical activity and sedentary behavior in 300 students from Berlin and Brandenburg, grades 8 or higher. And we want to identify also associated factors. And since this is a citizen science project, the role of students is of course crucial. And the main role or the key role is really that they help us, they develop together with us a questionnaire to assess potential influence factors of physical activity and sedentary behavior. And then they also participate in the data collection, but also in the data analysis and in the interpretation of the data. And this is an open science project. So the study data will be made publicly available on the study website, where then aggregated results can be created on the study website. Next slide. So the field phase of SMOVE looks like the following. We are visiting the school classes 3 times. We have 3 visits. Next slide, please. So during the first visit, first of all, we give a short presentation to the students. to introduce them to the health relevance of physical activity and sedentary behavior. And then the key point of this first visit is that the students develop a questionnaire interactively together with the scientists. And this you can see here on the picture, what that usually looks like. So the students spread out in small groups where they discuss and come up with up to 5 factors that they think are determining their physical activity or sedentary behavior. And then we collect this together and discuss it and group it. And finally, the students vote for the most important factors. And these are those that then go into the questionnaire. And then we also distribute the accelerometers. That's the active PAL device. It's the small orange device you can see here. It's slightly bigger than a €1 coin, and it's worn on the thigh. So we stick it to the legs of the students. They stick it themselves actually with a Band-Aid that is waterproof. So they are then asked to wear this device for 1 week, day and night. They can take a shower with it. They can basically usually wear it all day, except when they go swimming, they have to take it off, or when they do really physical contact sports. And so then they wear it for a full week. And during the first visit, we also distribute the questionnaires for the teachers and for the parents. Next slide, please. During the second visit, then we bring the questionnaire that was developed by the students and an established questionnaire. And they fill these questionnaires out, and we also collect the parents and the teachers' questionnaires, and we collect the accelerometers that they have hopefully been wearing for a full week. Next slide, please. And then during the third visit, what we do with them, we discuss the individual results of the accelerometer measurement. This is the picture you can see here on the left. That's the individual output that they get. Roughly a week after our second visit, they get this through the teachers via mail. And then we can discuss these individual results with them. And then we also show them aggregated class results and jointly discuss those together. That's of course also a good opportunity to give some input on statistics, and then we discuss that together and interpret this together. Next slide, please. So regarding the current status, so the preparation phase is finished. We got all approvals, like ethical approvals, data protection approval, and the approval of the school authorities. And our quite sophisticated, actually, study infrastructure is up and running. And we have participation agreements signed by 10 schools, and altogether we have 21 school classes who want to participate in the study. And these schools and school classes agreed to participate or expressed their interest to participate after public announcement to schools in Berlin and Brandenburg. And the field phase actually started in February 2020. We completed the data collection in 2 school classes until, unfortunately, the schools were closed during the first COVID-19 lockdown. So then, of course, the study was interrupted. Next slide, please. So what we did during the lockdown actually is that we worked on the questionnaires and the logistics. So we updated the questionnaires, first of all, to match the current situation, because the school situation now after the first lockdown is quite different and can be quite different. So now we have the opportunity also to ask for homeschooling, like sitting hours in homeschooling, for instance. And we also added some questions to find out what kind of determinants or behavior changed due to the pandemic, so they compare before and after the pandemic for certain determinants. And of course, we also had to update the logistics. So we now have a hygiene concept. We wear masks and use disinfectants and so on during our school visits. So luckily, we could restart the field phase in mid-September. And since then, we have collected data from altogether 4 school classes. And the 5th school class was finished the data collection this morning, actually. And our response rate is actually quite good in the classes. So once we go to a class, 74% of the students actually participate and fill out the questionnaires and also wear the accelerometer device for 7 days. Next slide, please. So I would like to show you just some very preliminary results. This is from the 2 school classes that we recruited or that participated in the study in February. It's altogether 33 students. They were between 14 and 15 years old, so they were 9th grade. And we had to exclude 3 students because the active file records were incomplete. So altogether we have here in this data set 30 students, 12 boys and 18 girls. Next slide, please. So these are the parameters of physical activity as we get them from the accelerometer device. So what you can see here, we have, for instance, the hours they spend sitting or lying. And here, and you have to keep in mind that they usually wear the device day and night. So this includes sleeping hours and also sitting hours during school. So that's how they come up. We come up with quite high numbers here, between 14 and 20 hours of sitting or lying. Then we have between 1 and 4 hours where they are standing, between 1 and 3 hours where they are stepping or walking, so where they are upright and walking. And we have also the step count that is comparable to the step count as we find it in other devices, like those wristbands. So that's between 5,000 and 16,000 in this group. And we have the sit-to-stand transitions per day. So that's actually what is recommended by the WHO, that the sitting hours are interrupted as often as possible. And you see here that we have a lot of these sit-to-stand transitions during the day. And we also have a measurement of energy expenditure. Next slide, please. So if we look at the step counts, there is quite well known, and we always hear that the students know that also, this threshold of 10,000 steps that apparently is recommended, but actually this is not really a biological threshold. It's just a threshold that was set in the 1960s, basically by a Japanese company that developed a device that counted basically 10,000 steps per day. And then because it's a nice and round number, I guess it was overtaken. And if we look at how many of the boys and girls met this 10,000 step criteria per day on average, this percentage is quite low. So 17% of the days had on average more than 17% of the boys had on average more than 10,000 steps per day, and only 6% of the girls met this criteria. If we, however, look on the step counts per day, so here on the right side of the column, we look at the number of days in boys and girls, and the percentage of days where this 10,000 steps were reached. So for boys, on 37% of the days, the recorded days, the boys had more than 10,000 steps, and for the girls, that was 17%. And then if we apply other thresholds, for instance, 7,500, which in adults has been associated with a lower risk of mortality if you have more than 7,500 steps per day. This this was actually then, it's a lower threshold, so this was met by a higher percentage of boys and girls. Next slide, please. And then finally, this is just to give you an insight on the questionnaire that was developed by the students. So in the discussion, it came out quite often that they say that the most important determinants for their sitting behavior is homework and social media. And so here are the results for the time. Then in the questionnaire, we ask them the time spent for homework on a school day and on a weekend day. And there you see that there's a wide range of minutes, between 10 and 150 minutes per day they spend on homework during a school day, but also up to 240 minutes on a weekend day. And the time spent for social media, this question was only asked in one of the school classes, because only in one of the school classes the students said this is important for our sitting behavior. And there you see that those numbers are actually quite high. So between 10 and 360 minutes per day of social media used on a school day, and between 10 and 480 minutes per day on a weekend day. And what was actually quite interesting for us was to see that it's quite easy for them to find out these exact numbers. So if they use the social media only on their phone, they just check on their phone the number of minutes where they have been using WhatsApp or Instagram or whatsoever, and then they write that down. So that was something that was actually new to me. Next slide, please. So just to give you an outlook, we are now fully booked and we will visit school classes until summer vacation 2021. I really hope that we will be able to continue our study during this phase of COVID-19. So we will see. And then one of our next steps will, of course, also be to make the study data publicly available on our study website. And also in 2021, we will start the scientific analysis on the determinants of physical activity and sedentary behavior in adolescence. And I put here some links where you can get more information. And then final slide, please. And with that, I thank you for your attention and I'm happy to take any questions.
Thank you very much for that. Let me just see if we have anything at the moment. It's usually a little bit of a delay. But yeah, I was just wondering, I mean, do you have any initial thoughts on what the causes might be of this, do you think social media, for instance, is a big factor? Do you think that's going to feature quite a lot in your final analysis?
Yeah, I think, I mean, it's actually something that comes up when we discuss the determinants or potential influence factors that we discuss with almost every school class. So this seems to be something that really plays a role for them. One other thing that I found quite interesting was that apparently also the adolescents go to the fitness studios quite a lot to actually, you know, build up their muscles. So that's also something I didn't think of before. So yeah, I think it will be quite interesting to look at those determinants that was their ideas. In the last school class, it also came up that having a pet or a dog probably that determines their physical activities. So there's really interesting input coming from the students, I would say.
It is. That's fascinating. Yeah. I'd love to talk to you longer about this. We have to switch over to the next presentation, but thank you so much for coming in and sharing that with us. And if you go over to the YouTube where it's being streamed live, I think there might be a couple more questions on the chat. So
okay.
Maybe you can answer them by.
I'll have a look there. Yeah, thank you.
Okay, thank you so much. And yeah, great. Okay.
Okay. Well, good afternoon, everyone, and welcome to a short session on open data. My name is Flynn, and I'm a project manager at Iseki Food Association. Iseki is a nonprofit based in Vienna, but with employees all over Europe. And our mission is to facilitate and encourage and produce lifelong learning in the food sciences. So I'm here today to talk about the open food sciences. And I'll start by asking and showing what exactly is data, and then what is open data. I have worked with data for years, even decades, but I went to Wikipedia to see the definition and was pleased to see that I understand it. Data is information. It's qualitative or quantitative, and it's about people or about objects. And there are many kinds of data. Some of us are researchers and we collect data, but as citizens, we also contribute data. For example, our buying patterns contribute to financial data records, and our health. I went for a COVID test today. Our health activities contribute to medical and scientific data. And we are also, all of us, I think, users of data. For example, we want to know what the weather forecast is. And in the old days, we wanted to know what travel options were available and what time they would be. So there's lots of data out there. And not all of it is open, but some of it is open data. And open is the idea that data should be freely available to for everyone to use and to republish as they wish. So this is the ideal, and we are there more so in some sciences or in some situations than in others, but this is where we are heading, I think. So I'd like to ask now 2 questions to my audience. I'd like you to go to this site that you see. I can also put it in the chat. Do you think that's helpful, Emma?
Yes, if you put it in the chat, I will put it in the live chat for the YouTube. So just.
Okay, great. So let's see if I can figure that out. Yeah, I got it. Okay. So there we go. There's the site and there's your pin. And I ask you to go there and go to this site on VoxVote, and you'll have 1 minute to vote yes or no. Have you ever collected data? And I do believe that I now have to go and make this live. Let's see. There we go. So the minute is clicking away, and you can get to this VoxVote site, put in the pin, and indicate yes or no if you have ever collected data.
There's that icon that with the turning the eye off under the seconds on the right.
There we go. Okay, thank you.
Yeah.
Yeah, so all of us have collected data. Okay, great. So let's go to the second question. And the second question is, have you ever made your data open? And we have another 60 seconds to say yes or no. Okay, so about half of us, 12 people voted, and about half have made their data open. Well, that's pretty impressive, I will say. And let me go back to my slides and tell you why I find that impressive. This is not the first time I ask this question. Let's see. And in fact, the time before when I asked it, how are we doing with the screen share?
Perfect. Yes,
Great.
lovely.
The time before when I asked this question was to a group of researchers in a Horizon 2020 project that is focused on open science. And you see 40-something people answered. And most of them had indeed produced research data, so that was not surprising. But question number 2 was a little surprising, that only 1/4 had ever uploaded their data to an open data repository. I asked the question a little more complex technical way last time. So most scientists working in this open science project had not made their data open. And perhaps even more disturbing maybe is that most of the scientists had looked for other people's data in an open data repository, although they had not shared their own data. So this shows us some conflicts, I think, about people, scientists' use of open data. And it brings me to the idea of open data and the idea of fair data, because open data means that the data is available without any copyright or cost associated. But fair data means more than that. Fair data means that the data is actually findable, and it's also accessible, interoperable, and reusable. So open data can be not fair, and fair data can be not open, because it can be findable, accessible, interoperable, and reusable, but only for a small research group, for example. And open data can be perhaps not any of the fair options. And in fact, I have, oops, wrong direction. I have here an example from a graduate school course on open science, where the students were asked to look deeply into publications where where the researchers had made their data open. And in fact, here's an example of what a student found. Download the data in the supplementary section marked Appendix A, supplementary data. The following are the data related to this article. What do you think you would find there? The data, right? But instead you find an XML file that says, see the author for data, with no information on how to see the author. So this kind of open but not fair data has led to a favorite term of mine. It's called open washing. So like greenwashing, where we know many companies that are not very green are pretending to be green or doing a small environmental effort and a big publicity about it, we have the same kind of thing in the scientific world, where some scientists, perhaps not because they are, what's the word in English, méchant, evil or want to be liars, but maybe because they don't know all the rules, think that they are open, but they are in fact not really open with their data. So looking for open data can be like going on a treasure hunt. Where is that data? And with that, I'll show a really lovely video where Emma herself is talking to us about how open data is like a treasure hunt.
One way to understand the concepts of open and fair data is to imagine that someone has told you that there is treasure, a treasure chest like in the old stories. Okay, so the first thing on hearing about this treasure is that you need to be able to find it. Where is this treasure located? Is it on an island? Is it up a mountain? Is it in a basement? So you need some kind of way of locating it and understanding how you can get there, a directory or a map. So once you know how to find this treasure, then you need to know whether you can actually get to it. Are there obstacles? Can you know, will there be wild animals or dangerous weather conditions? What would you need to do to be able to actually get yourself to that treasure? Say that you found the treasure and you were able to get to it, but are you actually able to find the key to open it? Do you have the ability to engage with that treasure chest in any meaningful way? It's no good if you have the old antique key and it actually takes a modern padlock. You've been able to find it, you've been able to get to it, you've been able to open it, but is it the treasure actually useful? Is it something that you can actually spend in any way? Or does it have any value? It's no good if it's coins with skulls on them, as in the picture, when what you wanted was crisp euro notes or whatever currency you might require. The price of gold might have plummeted, so that might not be any good. So you've got to be able to find it. You've got to be able to get at it. You've got to be able to open it. And then it's got to be something that can actually mesh with your own life. So we can see this as an analogy for the principles of fair data: findable, accessible, interoperable, and reusable. The data has to be findable. You need to know where it is, and that location needs to have some kind of meaning for you. It's fine if you know it is on a memory stick in your colleagues or another university's drawer somewhere, but that's not going to be very helpful if you yourself can't get to it. And this blends well with accessibility. So other obstacles, for instance, is there a license? Is there a restriction in terms of ethical or protocols that you might have to meet before you can access this data? Interoperable. Okay, you can access and you can find and access this, but does the data actually work with your software, your systems? If it was written on a software that's now gone out of date, or on one that your university or institution doesn't give, doesn't support, then that's not helpful. You found it, you can access it, but you can't actually use it. And then reusability, and this comes back to licenses. You can find it, you can access and you can work on it, but can you actually reuse it? Can you share it? Can you include it in your own research? You know, is it clear what those guidelines are? So you can see that there's a balance here between the data being open. For instance, it could be made available on a website. So that strictly speaking, it's open. But if you don't know where it is, you can't get at it, you can't use it, and you don't know how it relates to your own research, i.e. it's not licensed in any clear way, it's actually not useful in terms of reproducibility or you know, moving research forward in any way. So open and fair are not synonymous, and it's important to make that distinction. And open is not necessarily the best if it's not done in a way that reflects the FAIR principles. And conversely, you can have data that obeys the FAIR principles, so you can find it, you can access it, it is interoperable, you know, for instance, a README file, and it is reusable, it's got a license on it, but it's not open in the sense that it's not public. For instance, if it has any identifying information, or there may be commercial interests involved, it could be in a database where you have to request permission to access it. So in an institutional repository, for example, and you have to sign an agreement before you're allowed to access the data. So open does not mean fair, and fair does not mean open. The two things are, of course, sometimes the same, but not necessarily, and that's an important thing to remember.
So I close by talking about what we might do if we want to make our data fair and open. And I will honestly tell you that I haven't done this yet, although I'm looking into it really actively now. And making your data, or for me, what I find to make my data fair and open is that I need to choose a data repository where I'm going to put my data. And that's a whole other task. And here are just a few possible data repositories. And I need to understand even what a data repository is before I choose one that's useful. And then I need to organize my data in a way that follows the metadata principles of the data repository so that people can find my data. And it's not what another nice term I found, it's not a data dump where I just throw my data out there and say, check, now I made it open. So I need to find the repository that's appropriate, and I need to organize my data in the way that this repository requires so that other people can find it and use it. And I will then show a short video that's in French, but I did manage to put English subtitles on it. And this is about data repositories.
Les entrepôts permettent de stocker des données de recherche, d'y accéder et de les réutiliser. Il existe différentes catégories d'entrepôts. Les entrepôts propres à un éditeur, à une discipline, à une institution ou multidisciplinaires. À cela s'ajoutent d'autres particularités. Certains entrepôts acceptent tous les jeux de données, qu'ils soient ou non liés à des publications. D'autres n'acceptent que les données sous-jacentes à des publications. Des entrepôts mixtes reçoivent à la fois des publications scientifiques et des jeux de données liés ou pas aux publications déposées. On dit aussi de certains entrepôts qu'ils sont de confiance, car ils répondent à des critères de qualité. Ces critères leur permettent d'être certifiés. De nombreux entrepôts ne sont pas certifiés, mais sont cependant largement reconnus par la communauté scientifique. Alors, comment trouver le bon entrepôt? L'une des solutions est de passer par un annuaire qui recense des listes d'entrepôts. La recherche d'entrepôts pourra alors y être filtrée par critères. L'on peut distinguer différentes catégories d'annuaires: disciplinaires, multidisciplinaires et mixtes, qui contiennent à la fois des archives ouvertes et des entrepôts.
Okay, so with that, I wish all of you a happy search for a data repository and a happy work in getting your data organized in the way that it can go into a repository so that you can say for real that you have made your data open. If you want to talk about open data with me, I'd be really happy to. And there's my email, and you can find me on LinkedIn. Thanks.
Thank you so much, Katherine. That was a wonderful presentation, and I think it's safe to say that you had a slightly rough ride in terms of putting it together, but that was truly excellent, and I love the term open washing. And as we said the same, I think we're going to try and get that trending. So that was great. So yeah, I'm just going to check on the live stream to see if there's any quick questions. Sometimes there's a little bit of a delay, but even if we go to the break, maybe you can jump over to the live stream and answer any questions, by on the chat. Yeah, I mean, I guess my question to you is the project you work for, not the project, you said it was an NGO type thing. Do you make your data open through that project? Have you had any challenges with that?
Yeah, there are a lot of challenges, and they range from not knowing exactly what to do, which repository, how should the data be organized, so to really practical challenges, all the way up to the administration doesn't really support us in the sense that there is no, how do you say it? There's no like policy in our organization of this is what you do to make your data open. And it, I think, is similar to open access publishing, which I think we hear about later. But as it was years before, now I think we are all more familiar and know how to publish open access, and it is accepted, and there is policy at our institution for it, but not yet for open data. So it's really a big challenge.
Yeah, no, I agree. I think definitely that open data is kind of a few steps behind open access on the sort of development. And I still think there's a lot of fears and structural work that needs to be supported through the open science movement. So yeah.
Fear is a good word. I should have made a stronger point about that, because in the open science project where ISECI is working, my institution, that is, I think, the #1 response we get from researchers is that they are afraid that others will take their data and use it before them or use it in ways that they don't support, and they don't feel confident in the different ways of copywriting or protecting their data. And I think this is something we really need information about.
Yeah, absolutely. I think that's a great note to move out to the, well, again, we're slightly behind time, so we might just go straight. But Katharine, thank you so much for your talk. And I learned some great terms and I think in the coming months and hopefully not too long, not years, months maybe.
Okay, thank you so much, and thank you for inviting me to present this project. So this is a project that should encourage people, or at least research how to encourage them to share their own genes, so that scientists could actually benefit from that, and that people would learn more about their own genomes. But the first thing I basically, can I just next slide? So the first thing just to put you on board is, like, when we talk about the human genomes and we talk about genes, what do I precisely mean? So, and when I talk about the molecule of DNA. So the human genome is basically a set of instructions to build basically us. So very complex human organisms such as Emma or Katharine or me. And it's written in 3 billion letters. But as compared to the English alphabet that consists, I believe, of 26 letters. Am I right? Because the Croatian one, I'm coming from Croatia, Croatian one is the 30 letters. So the English one, the human genome one is basically 4 letters, and we are talking about the A, C, G, and T. But that cookbook is actually huge. So these 3 billion letters would correspond to couple of thousands of books that are written on 1,000, like each of them consists of 1,000 pages with 1,000 characters. And if you would consider that, like, to add all these letters one next to each other, the human genome would be of a length of basically 3 meters, but it's folded in such a way that it's in the cell that you don't see itself per se. So it was interesting for many decades to understand how the human genome is written. So approximately like 40 years ago, scientists initiated the Human Genome Project with the idea to sequence the human genome. So after like almost 2 decades of research, they announced the human genome. In 2001, it was the former American President Bill Clinton who announced we have the human genome. But one of the scientists who was involved in the whole story said, the human genome, I bought the book hard to read. And what he meant by that is that we don't know how to read the human genome. So we don't know where where there is a beginning of the sentence, where is the end of the sentence. So in English, you will have the big starting letter, and you will have a dot at the end of the sentence. But in the human genome, you don't have the big letters and the dots. At least we needed to learn how to basically decode the human genome and understand where the protein starts, what are the regulatory regions in the human genome, and so on. So we have a lot of still, so almost 20 years after this initial sentence, human genome hard to read, we still have lot of research to do about the human genome. So if you would be interested as a citizen to analyze your own genome, so actually to get the information about your own genome, so what do you need to do? So there are a couple of companies that are offering sequencing or genotyping of the human genome. So genotyping means that you identified certain positions in the genome. So approximately 300,000 or up to 1 million base pairs in the human genome, which would correspond to a low percentage of your genome actually. And sequencing would mean that you get information about every position in your genome. So this is what you see in the slide is basically my family. I made them do the test. That was my Christmas present actually for them. You can even see in the background that there is a Christmas tree. So I tested them and I was curious to see how our results would compare. Not if they are my mom or if they are my dad, but if the company per se is doing the good job. And I was just interested to get information about my genome. So one of the, okay, I'll go to that slide back. So one of the information that I got is about my ancestry. So I've learned that I'm very pan-European person, but not just located to one certain region in the Europe. So I'm coming basically from Croatia. I would expect to get more, but my ancestors, like my grandmother and grandfather, are coming from the German Poland region. So that's not something very exciting. And my grandma from the other side is from Hungary. So that's something I can see on this map. Except for that, basically, I didn't get any other information. So I could get information about my genome, but I couldn't get more information about certain phenotypes that would be interesting for me, such as like, am I prone to be lactose intolerant? Am I prone to get certain either disease or a phenotypic trait or so on? But the company I used to genotype my genome did not provide that information. There are other companies, for example, there is 23andMe, and this veteran is a friend of mine. He's actually a colleague of mine who did genotyping as well. And he was very excited to learn that he's 0.1% Japanese, which when you have such a low percentage, then I'm like very questionable if that is really the case or not. But on the other hand, he could get more information just because the company he used provided more information. So he could get information like about the maternal mitochondrial DNA, what's his chromosome Y haplotype. You can actually get information about the Neanderthal ancestry. So how many variants do you share with Neanderthals? So they claim, you know, what's the percentage, how big Neanderthal are you? How many Neanderthal things there are in your genome? So if you use different companies, you get different amounts of information. And me as a bioinformatician was like curious to get more information about my genome. So I started writing a software that allows me to analyze my own genome. And then I did it in open source way to develop basically an R package that other people can use. So all our packages and pieces of software are open source, and anyone can download and use it. So we use it as a scientist, and citizens can use that because of their own interest. So I just basically, when I started doing, then there were just very simple functions, how just to import your DNA and then overlap it with certain databases that are offering information about how your genome is associated with a certain phenotypes. So the SNPs that you have, whether they are associated with certain diseases and traits, or they're not associated with certain diseases and traits. And there are just like basic tests there that can tell you whether you are like lactose intolerant, what would be the coffee consumption. So those tests are, I would say, kind of almost copy paste from the company-based tests, but they are offered only by one company, by 23andMe. So people who do have their genome accessible, they cannot get that information. So with this piece of software, they can get that information as well. So basically, the idea was to develop a software and give people opportunity to play with their own genomes, and then see how interesting that would be for citizens. Just a sec, I'm going to go couple of slides back. So this is not the only initiative that is trying to associate like open data with open science and genomes. So there are a couple of others. One of them is Open SNP Initiative, which offers people to just like upload their genomes, and scientists or any other citizen can download your own genome and perform certain either bioinformatical analysis or scientific analysis, or just like learn to play with the genome. Even, for example, if you don't have your own genome, you can download other people's genome and play with it. There is an Open Humans Initiative that is trying to like, that became kind of umbrella initiative that is combining all previous, like the Open SNP, but allows scientists to create projects and encourages people and scientists to track their data using different devices and to combine them with the genomes and genotypes. And the last one is a Personalized Genome Project, is from Harvard University, that is as well trying to encourage people to donate their genomes. So one of the things why that would be interesting, especially in this time, is because at the moment, there are approximately 20 million people who genotype their genomes, which means that it represents a huge scientific resource that is currently not used by scientists. And it would be interesting to realize why. So why it's not used by scientists is because people don't share their genomes. So they genotype their genomes, they get the analysis from the companies, and they stop there. So they don't use it in any other way. And nowadays, it would be super interesting to have such information about people's genotypes, because it could be combined with information about corona infection. So to get genetic susceptibility of corona, so people would in that case share information about their phenotype. So did they get were they infected by corona, and what were the outcomes of that? So what were the symptoms? And then combined it with the information about their genomes. So if people would share, you would already have probably 20 million pieces of information. Did they get, they didn't, and what would be. So that's from my side. Thank you very much for listening. And again, Emma, thank you for inviting me. And I would like to get your questions if there are any questions.
Great, thank you so much, Inga. There's sometimes just a little bit delay because there's a 20-second delay anyway to the YouTube. So yeah, I mean, obviously when I was kind of looking at this work that you've done, you were looking at applying it to a citizen science project. And I'm just kind of wondering, like, what you think the future holds for you personally with this work.
Well, it was an interesting experience for like applying for the citizen science project and not getting it, and then finding the advertisement online that University of Edinburgh got the same project.
Right, yeah.
And that was like, wow, it's just like, the project is great. And I mean, it's an important project. And it's just like the matter, someone else got it.
Yeah.
So they were extremely focused on the aspect of like understanding, trying to understand how to encourage people to donate their genomes.
Right, sure.
Yeah, because it's affiliated basically with a project called Corona Genes in UK. And basically they want to do the same thing to understand how to encourage people to get their genomes. Nonetheless, so I think this piece of software is something that still needs to be online and that will be now or later on interesting for people. So from my side, I am planning to like continue developing it when and one of the directions, so basically the software at the moment is written for analysis of a genotypes, but later on it will be interesting to be so that people are basically able to analyze their genomes, like the full genome sequencing data.
That's very cool. Yeah. One question that's come up, well, two people have actually raised it. Is there any data security issues with sharing genotypes?
So data security issues, I would like to know precisely. From
it's quite broad, right? Yeah.
Yeah, it's a quite broad question. So
I guess people are concerned about if they upload their genetic data to any kind of cloud or computer, that could be somehow stolen and used in some way or shared without their consent. Or I think people have I personally was quite reluctant to do one of those heritage things. I did in the end because of lockdown boredom. I was like, well, I'm gonna got nothing else to do. I'm gonna spit in a tube and see where I'm from. But I was hesitant. I was like, what's gonna become of this? Who's gonna have access to it?
So there actually, I can answer this question from two aspects. First, from just like obtaining your data. So what you said, you were reluctant to actually get it. So it depends from the, like different companies have different policies. And I used one of the companies called myDNA that says, if you want to get your, like you do the genotyping, if you say you just want to have your data, they delete your data from their database. But for example, my ancestry is they have in their disclaimer basically that they own this data. Even when you die, it's still there. Wow. So it's still in their database. So I think if you're interested to do something like that, then you check from the company to the company. So what happens with your data? On the other hand, from the aspect, if you want to do later on something with your data set, I think many people would be concerned about like maybe insurance issues, that maybe later on there will be like discrimination based on your genome.
Right.
And I wouldn't elaborate now much further. So it could happen. I mean, it's that's a big ethical question, and it's raised, and it's like there are a lot of discussion about that. So that could be a problem. Nonetheless, for example, if you use Open Humans, they have the whole pipeline how to basically make sure that everyone has their data and they don't share it, so that other people cannot access their data sets. So they have like developed the pipeline how to code the data set so that people can, as a scientist, can still use it, but not that it just like points to the person.
Okay, yeah, I understand the distinction. Yeah, yeah.
Can I-
Marja, did you have a
Yeah.
question? Yeah.
Yeah, here is Marja Pirttivaara from Finland. My warmest thanks to you, Inga. This presentation was really interesting. You see, I'm enthusiastic with genome data and analysis and genetic genealogy. I have written a book about that in Finnish, and in Finland we have very active genetic genealogy community. Like I'm coordinating a project of Finland DNA at Family Tree DNA. Within that, nearly 20,000 people. So I have my hands on in these issues, and I have my DNA has been analyzed by all of the biggest companies. I'm cooperating with them. I have even my whole DNA analyzed in Dante Labs, also with this artificial intelligence report. They've in a way establishing their report. I was a kind of test person for them as well. So I think I will contact you, send you an email, etc. We can discuss about these things. It's wonderful to find someone who is really interested in these things. And as I wrote there, with this Open Humans Foundation and Open Humans, I'm so happy to see that you know that and are interested in that. I'm a member of the board of Open Humans Foundation, so this is very close to my heart as well. So really interesting.
Yeah, thanks. I'm looking forward to communicate, to continue communicating.
Yeah.
That's awesome. And
That's
Katherine has a hand. She raised her hand as well.
Is there any other questions, or I think that was
Okay.
it's gone back down again. Okay. I think that was what Marja wanted to share with you. So I'm so happy that the Open Science Cafe is now a networking event as well. They said it couldn't be done on Zoom. They said networking couldn't be done on Zoom, but we've just proved it wrong. Okay, well, on that lovely note, I think we will go for a little break to make up for time. But thank you, Inga, for coming and sharing your research and your work and your insights. Excellent. And yeah, I'm sure we'll be in touch soon to do something else where we can showcase your work.
Thank you so much for inviting me.
No problem. All right.
Bye.
Hi everybody, my name is Mary Anderson-Glenna and I'm from the University of Southeastern Norway and I'm going to co-host today with Emily.
Hi, and I'm Emily Farran. I'm from the University of Surrey. So I'm going to start off by talking a bit about what open content is and what it might mean to you, and then Mary's going to go into the different kinds of licenses and the history of open content. So what is open content? You'll see I've put some images there of different places where you might have accessed open content. So it's content which is any kind of work that you can use, copy or modify by attributing it to the original creator without needing to ask any permission. So you might have used things from Wikipedia, YouTube, Flickr, and lots of other things as well. And there are different ways that you might classify the types of open content in terms of the 5 R's, in terms of how freely you can use them and the permissions that you have. So it's to do with whether you're allowed to retain your own copies, whether you can reuse it, whether you're allowed to adjust it, so revising it, that's the 3rd R, whether you can remix it, so whether you can combine the original with other open content to create something new, and whether you're allowed to redistribute it. So Mary's going to go through different licenses which all kind of relate to different versions or different levels of open content which relate to these 5 R's. Why do we have open content? What are the benefits? Well, you might have yourself been able to freely access things without having to pay for it. It by virtue of this, it increases access to all in terms of widening participation. There's no financial barrier for people to access things and no geographic barrier as well. If you're using it to create your own material, it can reduce the time that it takes you to do that. And also it might enhance your material because it might give you ideas as to what else to include in whatever you're creating. And in doing so, it stimulates further content because you might then create something and make it open for others to use yourself. It allows rapid dissemination of information because there aren't that many steps to go from you creating it to others being able to access it, which is different from other sort of processes where there might be lots of different steps which enable it to get out into the wider world. And that, because of that reason, and the fact that you're the one that's put it up there, it's more likely to be up to date. So for example, open textbooks, if there's less steps to get it up there and the person who's written it is able to keep it up to date, then there's a real benefit of using open content textbooks, perhaps over closed context textbooks. And textbooks is one example. It also allows you to collaborate because things that are open, as we've seen in the previous session, it allows people to kind of see what other people are up to and collaborate and network with that. So have a bit of a think. Have you ever used open content? So have you used a video? Have you used a picture? Any text for something that you're creating? So if you're creating flyers for something or using it in your teaching. And did you think about how you knew you could use it? So just going by the images that I had as examples before, Wikipedia, Flickr, YouTube. So for each of those, most of them would be, you can search whether they're licensed under a Creative Commons license. And Wikipedia uses a couple of different licenses, which we won't go into all of these today, but we'll certainly go through the Creative Commons licenses. And something I discovered myself while creating these slides is that in some search engines like Google and like Yahoo, you can actually do a search which specifies that you only want things that have a Creative Commons license. So I've just put a screenshot in here where I searched for an image of a car, and I could make sure that all of the things came up would be things that are open content that I can use under a Creative Commons license. So what about the other way around? Have you ever shared your work? Did someone use something that you created? How did you share it? How did you know that it was, how did they know that it was okay for them to use it? So you might not have thought of this so much, but if you did want to share your work, you can use the Creative Commons choose a license tool. So if you just Google that you'll find the tool, and it asks you a number of questions so that it'll help you choose which license you need. You can upload things to open content places like SlideShare, Flickr, YouTube. And if you're doing research, then the Open Science Framework is somewhere you can upload all sorts of things from your data to your output to your tasks, etc. And I just took this from the Creative Commons website. This shows lots of different places that use Creative Commons licenses where you can upload your open content and give it a Creative Commons license, and then people can search for it under that particular license. Okay, I'm going to hand over to Mary to talk about the history of open content.
Thank you, Emily. We thought it was a good idea to bring in the history perspective because open content isn't new. It's been discussed a lot these days, and it's great that there's so many of you attending this session on open science and open content, and that shows you how open content is becoming more and more mainstream. But the original concept itself was developed by Michael Stutz in his paper on applying copyleft to non-software information while he was working on what was called the GNU project, which was a project on mass collaboration for free software. So that's sort of where it started. And then the term open content itself wasn't coined until 1998. By David Wiley. And this basically was the start or the birth of Creative Commons, which was established in 2001. So Creative Commons is an organization, it's a movement, and it's also a set of legal tools or licenses, as Emily has mentioned a couple of times already. And the whole sort of movement for Creative Commons is really all about believing that knowledge and creativity should be open and shared and built on, and that everyone has the potential to contribute and to this creativity. So open content has continued to evolve with other movements. For example, the Open Knowledge Foundation, which is a non-profit network promoting the free sharing of content and data, and the Free Cultural Works project. And these are just some examples of how it's continually evolving. Next slide, please. So first thing I will say is, did you know that every photo you create, story you write, song you write, or every one that is created automatically has all rights reserved copyright? And if others want to use it, they have to ask your permission. And that can be rather tedious if there's an image you've created that's very popular and you're getting 100 emails a day to ask you if it's okay to use your image. So Creative Commons allows you to basically retain your copyrights, but to put more flexibility in your license, or more flexibility in the use of what you've created. So it enables you to also retain the rights to your work and also get acknowledgement for that work. So Creative Commons licenses themselves are built up of 3 different layers. So you've got the legal code, which very much looks like a copyright law type of documents that the lawyers like, that we don't really read, fine print, you could say. But then what's very good with Creative Commons is that it has what they call a commons deed, or a human readable form, which is really for those that are not used to the legal jargon, and consists of a summary of the most important terms and conditions, and also a symbol, so it's easy to recognize which type of license that it is. And then we also have the 3rd layer, which is a machine readable layer. And that's with Emily giving her car example, how you're able to search on search engines specifically for those images, for example, with Creative Commons licenses. Next slide, please. So now we go a little bit into the more technical side of it with the actual license types. And what types do you find? So there's 6 combinations basically of Creative Commons licenses, and they contain different combinations of what's called license elements. And this is a little bit back to the 5 R's as well that Emily mentioned, with refining, reusing, revising, remixing, and redistribution. So you'll see that there's different elements here telling you what you can actually do with, for example, an image, which rules apply. So what I will say is that there's a spread that goes from all rights reserved, which you see at the bottom of the image, the whole way to Creative Commons 0, which is basically all rights have been given away. And there's into the public domain. And there's not so many examples of that, but what is a good example is, for example, old pictures, paintings, which have been around so long that the rights are no longer there. And now, for example, Claude Monet painting that is hosted by the Art Institute of Chicago is out there for everyone. They've put a high resolution image that people can use under a Creative Commons 0 license, or open in the public domain. So what about the other types of licenses then? So the most open would be the CC BY, Creative Commons BY, or Creative Commons BY, as I say, which is basically an attribution license, which means that you can modify, redistribute, build on the original, but you have to acknowledge the original creator. And then you have different variations on this. So say, for example, you have an image that you've downloaded a photo and you want to do something with that, you want to modify it, then that's okay under the CC BY SA license. But whatever modifications you make, you have to inform of and use a share alike. So you have to share under the same license. Whereas the next license here with ND, no derivatives, means you couldn't modify that image. And then the NC, for example, is non-commercial. So it means that you can, in this particular case, you could modify the image, you can reshare it, but you cannot do anything that you can earn money on, so not commercial. CC, BY, and CSA, so getting more letters as we go along, getting more strict. You have to give attribution. You can't use it commercially, and if you make any modifications, you have to share under a similar license. And then the last one is so strict that it doesn't allow you to make any modifications. Next slide.
So I'm going to talk now just to, thank you. So one type of open content or open educational resources. So these are kind of open content that I'm sure most of you have heard of, but it's any kind of educational materials that are out in the public domain that come under one of these licenses. So it could be textbooks, curricula for a course, lecture notes, and we've listed a number of different types of open educational resources there. So what we're going to go and do in the next couple of slides is just give some personal examples of when we've come across open content in our own lives. So for me, when I started publishing preprint, so this is where I'm sure in this kind of pandemic, everyone's heard of a preprint, but so preprint is when you upload the kind of Word version of your paper for open access for anyone to read. And when I went to do this the first time, it asked me the question, what kind of license do you want? And I thought, I don't know. So hopefully anyone who's been to this talk will, when you come across this kind of dilemma, you'll know just to look up the Creative Commons licenses, and you can work it out from there as to what kind of license you want for what you're uploading. And then during the COVID-19 pandemic, when we had restrictions, and in the UK, the schools were closed for 4 months, and we were being sent stuff home by the schools for our children to do at home. And many of the things that we were sent, the schools hadn't paid for. They were accessing this open educational material. So for example, in the UK, many children used White Rose Maths and were listening to open access lessons on the Open National Academy. Okay, over to Mary for a couple of examples from her.
Thanks, Emily. Well, one of the examples is, that I have here is basically having open content allows you to actually take courses, for example, that you wouldn't have the ability to take otherwise. It also allows you to take courses with some of the best universities in the world, for example, with MIT and Yale. And from my own personal experience, I had a career break, basically a career gap between my postdoc, and I went on to my next research position. And I wanted to go and work in a research institute, and I needed to have project management skills, which I didn't have, and I didn't have any knowledge about project management either. So I used the MIT OpenCourseware to actually educate myself for project management through their open courses. And that was a great opportunity because I wasn't near a major city. I wasn't near good libraries. I didn't really know if I could trust. There's so much information on the internet that you don't really know, what's the right place to go and what's the right information. So I wanted to have something that I could say, okay, well, I know this course is going to be good, and basically train myself up and got the job I wanted, because then I could like relate to project management and talk about that in my job. So that's great. And it's courses home to you in the Corona times. Again, it's a fantastic opportunity to be able to use this to educate yourself if you have an opportunity when, for example, there's a lockdown. And the same basically applies with my second example. That's basically, there's a number of websites that have, for example, open textbooks, and that both provides an opportunity for those that maybe want to add to their knowledge, but also to students who maybe want to read up on certain things, can't afford to buy a textbook, maybe again aren't so close to major libraries. Now with the digital learning, it's not always that you're close to facilities. So OpenStax, for example, has a number of textbooks in a large number of disciplines, and is growing. And then we've also got something called the Open Educational Resource World Map, which is the bottom link here. And that is open educational resources and is continually being built on. And they have a vision, as they say themselves, of facilitating the exchange of data and experience and ideas between open educational actors and communities. So these are just a couple of examples. And that's basically what I had to say as well. So I think that opens up for if there's any questions.
Lovely, both. Yeah, so like I said, there's a slight delay. So there may well be some questions in a moment. But yeah, no, that was a lovely presentation. I really like the examples at the end, of real life examples of when people have utilized it, because I don't think people maybe realize how much we rely on open educational resources like that. And I think there's sometimes a little bit of confusion. I mean, I was saying to some colleagues, well, a colleague was saying to me, you know, before we started working on open science, did we even think about whether it was okay to use a picture or not? Yeah. I guess my question, I don't know if it's more of a comment than a question really, but I guess my question is, do you think that open licenses are something that are becoming more mainstream rather than something simply to do with open science, whether it is actually becoming something that people use in their everyday life?
Absolutely, Emma. And I can just say I was amazed myself when I read that there's now currently 1.6 billion Creative Commons licenses, and it's definitely not all by scientists. So I think this is becoming very mainstream. And I can tell you that if I was a photographer, if I was a writer, I would be looking into using Creative Commons and the whole world opening up with collaborative opportunities, getting your work out there, getting recognized. So I think this is for everyone who creates. Yeah,
art as well as science, I think, is definitely benefits from this. Just check. Yeah, so we haven't got any more questions at the moment. I think people, whenever I've talked about Creative Commons licenses, people need time to kind of think about all the letters and what they actually all mean. It can be a little overwhelming at first, but I mean, actually, it's not, is it? It's actually quite easy to use it.
And I think that one of the factors is that originally, you know, whenever you see the Creative Commons, like which license are you going to use? You think that this is, am I going to have like 100 licenses to choose from, or you know, they're not, people are not so sure. So I think that it's a comfort in a way that to know that there's not so many license types under Creative Commons. As Emily pointed out, to be able to go to a site and read on it, and it is, you know, that Creative Commons do a great work in actually making it understandable.
Yeah, I think they've even got a thing now where you can like click what you want and they generate the license for you. So you don't even have to pick out of a list.
I was looking at that yesterday. So there's just like almost like a questionnaire, and at the end it says this is what you're after, kind of thing.
Yeah, which is brilliant. It makes it very user friendly. So you just need to go to the thing.
Great, thanks, Emma. So hi everyone. My name is Steve, and in my day job, I'm a research services librarian at the University of Manchester Library, which is in the UK. I am currently sat in my spare bedroom in a house in a place called Burnage, which is about 4 or 5 miles south of Manchester city centre. And the weather here is kind of uncharacteristically quite pleasant today, although it's quite cold. So if you see my blanket at any point during the presentation, then that's why I'm kind of covering myself up to protect myself from the cold today. Anyway, you don't need to know about that. As I was saying, my day job is as a research services librarian, and in that role, I support researchers to make their publications openly available. And that's what we'd usually refer to as open access. And I've been working in open access for about 6 years now. And as a result, I think I'm reasonably knowledgeable about that particular facet of open science. Today, however, I'm stepping out of my comfort zone slightly, and I'm going to be talking about a different facet of open science altogether, though I believe some of the principles are the same. I'm going to be talking about open hardware. Now, to give you a full disclaimer and to manage your expectations about this talk, I am not an open hardware expert. So this will be a very basic introduction to the subject. Now, if there are any open hardware experts watching the YouTube stream today, you have 2 options. You can either go make yourselves a cup of tea and come back for the open source talk at 4:30, or so 5:30 in European time, or if you'd like to stick around, you can contribute to the session by providing your insightful comments in the YouTube chat. I'm sure the other attendees would love to hear from an actual open hardware expert, as well as me providing my introduction as well. If you don't know much about open hardware, then do keep your eye on that chat, just in case anybody is providing any nuggets of wisdom. For those of you who are going to be sticking around, here is what I'm hoping that you'll have learned by the time that I have stopped talking. So after this 15-minute talk, I would like you to be able to define open hardware as a concept and maybe identify some parallels with other open science practices that you might be more familiar with. I'd like you to be able to summarize some of the benefits of open hardware. I'd like you to understand how open hardware is being used and by whom. And I'll give you some examples about some open hardware projects, but I'd encourage you to do your own research after today as well. And I'd like you to be aware of some open hardware resources that you can use and potentially signpost people towards in the unlikely situation that you're ever asked questions about open hardware. So let's get started. Well, whenever I talk about open access and open research data, I like to kind of take a step back and talk about openness more generally. And when I do that, I like to use this quote from Ursula K. Le Guin. In her novel, The Dispossessed, she talks quite a bit about the importance of sharing knowledge widely. And she says that it's the nature of ideas to be communicated, written, spoken, done. She says that the idea is like grass. It craves light, likes crowds, thrives on crossbreeding, and grows better for being stepped on. And what she's saying very eloquently here is that knowledge is strengthened when it's shared amongst a large number of people. It's strengthened by being scrutinized by those people, and it's strengthened by being kind of combined with knowledge from other sources. So pre-existing knowledge and biases all kind of feed together to strengthen knowledge and eventually make the world a better place. So when I talk about open science, I, much less eloquently than Ursula K. Le Guin, see it as being about removing barriers. So whether that's barriers around the price, so making sure that people who are accessing content don't have to pay for that privilege, barriers around permission, so making sure that people who want to use that content can do so without worrying about breaking copyright law, and then other barriers around discoverability and comprehensibility, and probably some others that I haven't thought of yet. So it's all about removing barriers, and the aim of removing those barriers is to make it easier for your audiences to find, use, and build upon existing knowledge. But how do we facilitate that? Well, we do it through open licensing, and there's just been a talk about open licensing, which is really interesting, and I hope that you learned a lot from that. We do it through infrastructure, so that's systems and databases that we use to share this content openly. And we do it through standards, so we have standards around how to describe the open content, but also standards around how we help people make use of that open content. And some of these things will get surfaced as I go through my slides today. So that's kind of openness in general. That's the kind of philosophical start to the presentation today. But over the weekend, I had a theory, and I just want to share with you my kind of thoughts about the position of open hardware within the open science community. So I've worked in open access for ages, as I said, and I predominantly speak to people who work in adjacent disciplines, for example, open research data. And I was interested in whether there was a high degree of familiarity with the concept of open hardware within those communities. They are, after all, open science communities. So I was interested in finding out how much those people knew about open hardware. So I took to Twitter a very kind of rigorous data collection method and asked this question. I asked people, how familiar are you with open hardware as a concept? And I asked them to kind of grade themselves from 1 being not at all to 5 being I am an expert. And the results kind of supported the thesis, the hypothesis that I'd come up with earlier, in that there doesn't seem to be very much crossover between open hardware and the rest of the open science community. But 15 people, particularly a strong sample size for the researchers out there, out of the 15 people, 11 people rated themselves at 1, and 4 people rated themselves at 2. So nobody considered themselves particularly knowledgeable about open hardware, which I think was interesting. Then I asked them a follow-up question. I asked the same respondents to name just one single open hardware initiative, project or product. They didn't need to give me any details about it, they just needed to give me a name. And there were two camps really. The first camp were people who very sheepishly, in some cases, admitted that no, they didn't know any open hardware initiatives, projects or products. And I think that kind of goes to support my theory that there isn't very much crossover between those two parts of the open science community. The second camp was, I think, just as interesting in that they all gave the name of the same project. They all said Raspberry Pi. And what's interesting about their responses is that all three people who named Raspberry Pi did so while making it clear that they weren't entirely sure that that was the case. So the first person put Raspberry Pi, ? The second person said Raspberry Pi, is that open hardware? And if you're asking a question in the answer to a question, that suggests that you're not terribly sure of your answer. And the third person just came out straight away and said Raspberry Pi, and this is a guess. So there was some awareness of Raspberry Pi as a thing, and people kind of thought that it might be open hardware, but they weren't sure. And I'm going to park that subject for now and come back to it a bit later. But if you'd like to comment in the chat, if you're watching on the YouTube stream, about whether you think Raspberry Pi is an open hardware project or not, yeah, go for it. I'd like to see your responses. So let's park that issue for a second. And we've talked a bit about openness and what that means. But when we're talking about open hardware, what exactly is the hardware that we're talking about? Now, for people like me who work in open access, it's very easy to visualize what opening that open content involves. When you're talking about digital files, it's just a case of removing password protection and allowing people to download those files from kind of online databases or repositories. But making a physical, tangible object open seems like a much more difficult thing to get your head around, doesn't it? And I'll talk a little bit about what exactly this means in a moment. But when we're talking about open hardware, the hardware really can refer to any number of objects. And these are just some examples, not a prescribed list, but they could be computers, prosthetic limbs, clocks, chairs, engines, anything you can think of really can be opened up. And now, about 10 minutes into my talk, I'm going to define open hardware for you and hopefully bring you back round if you are starting to lose interest in this presentation. So from opensource.com, which I found a really useful tool in researching this subject, they define open hardware as being something that refers to the design specifications of a physical object, which are licensed in such a way that said object can be studied, modified, created, and distributed by anyone. So it's not the physical object that is being made openly available. Someone isn't driving around to your house and dropping off a prosthetic limb on your doorstep and saying that it's yours. What they're actually doing is providing you with access to the specifications, the schematics of that object, and giving you what you need to construct it for yourself. So I've kind of come up with this metaphor, which is not particularly original when it comes to talking about open source things, but I've gone for it anyway. So open hardware is kind of like sharing a recipe. In a recipe, you're given all the information that you need to make a dish. And it's entirely up to you what you do with that information. You can adapt it if you like. If you want to leave some ingredients out or add some extra ingredients, you can do that. If you want to follow it to the letter and recreate the dish as it's presented, you can do that. And if you want to share your adapted recipe at the end of it, you can do that as well. But again, you're not being given a free bowl of soup. Someone's just giving you what you need to be able to make that soup. And again, from opensource.com, they provided some rationale around why people would even think about kind of making their hardware openly available. And they provided the kind of criteria for what we would consider to be open hardware as well. So they say that open hardware should allow anyone to have the freedom to use the device for any purpose. So there should be no restrictions on what you can do with that device once you've constructed it. They should also allow people to study how it works and make any changes that they see fit. They should allow the redistribution of the design and of the device and the device itself. So what you do with that device after it is none of the original creator's business. And they should allow you to enhance the design as well as the device and make those improvements freely available to the public so that all can benefit. So once you've kind of refined the design that you've taken, you should make that adapted version available as well. And I use the word benefits there, and maybe it'd be useful at this point to talk a little bit about what the benefits of making hardware open are. So making hardware open, as it says here, potentially enables collaboration with significantly more people, all offering feedback and helping to improve the development of a project or product. It's the wisdom of the crowd, and I was talking earlier about encouraging experts to join in with the group chat on YouTube. And that's the same thing. We're benefiting from the expertise of many more people than we could feasibly ever meet and talk to in real life who'd be able to contribute to the projects that we're working on. And it has a role in teaching and learning as well. So open hardware provides an easily accessible way for students to learn about all kinds of engineering. To kind of go back to my metaphor of the recipes earlier, how do you learn to cook if you don't have recipes to help you kind of put together your first meals? How do engineering students get experience of building things if they don't have the kind of designs and schematics to help them construct things? So I said, I teased a little bit earlier and said that I was going to talk about Raspberry Pi and whether that is actually an open hardware project or not. Now, if the three people who contributed to my survey are in the room today and they wanted confirmation about whether a Raspberry Pi is open hardware, I can now confirm that it actually isn't. So it's easy to see why that might be kind of mistakenly thought of. So the schematics for the circuit board, as you can see on the screen, are openly available. They make those available on the Raspberry Pi website, but it uses proprietary CPU chips manufactured by a company called ARM, I think. And those chips are not open source. And if you want to get hold of the schematics for those chips, you would have to sign a non-disclosure agreement, which isn't very open. But on the other hand, Raspberry Pi does run on open source software, and they're often used to help young people, especially, learn how to program. But I won't talk too much about open source software because that talk is coming up later, I believe. So Raspberry Pi isn't an example of open hardware, I'm afraid. But if Raspberry Pi isn't an example of open hardware, maybe we can talk a little bit about some actual examples of open hardware. So here's a couple of examples of things that I found from looking about on the internet. So on the left-hand side, we've got an image from the open source bionic leg project. This is a team of researchers at the University of Michigan, I believe, who have constructed a bionic leg, and they've made the designs and the schematics for those bionic legs available so anybody can construct their own. And by doing so, they're encouraging collaboration with a huge amount of researchers around the world who can all work together, scrutinize each other's ideas, and work together to eventually build a much more effective bionic leg and ultimately help amputees who might need such a leg. And then on the right-hand side, I've got some images from an article that was published in PLOS Biology recently. And this article is all about how open hardware is being used as a tool to fight against coronavirus. So in these example images, we can see PPE equipment that has been constructed with the help of open hardware. Now, from the very basic kind of PPE in figure A, which is basically a face mask, which instructions have been posted on social media for. So you might have seen it over the summer, people posting instructions for how to make these face masks. That is, in its very simplest form, an open hardware project. But also we've got more complex PPE in this image as well, from kind of more kind of technical masks to really complex equipment at the end of that spectrum. And these are all made possible through the sharing of open hardware designs. This article also talks about lots of other innovations in open hardware that have helped to fight coronavirus as well. There's some really interesting stuff about open hardware ventilators. I know in the UK at the start of the pandemic, the government was really quite concerned that there wouldn't be enough ventilators available in the National Health Service. So manufacturers were encouraged to turn over their production processes to building ventilators for use in hospitals and other healthcare settings. And to make that possible, the designs for these ventilators were shared openly. That's an example of open hardware. But I'd recommend you have a look at the article to see what other open hardware projects are kind of working towards fighting this virus. So as I'm starting to approach the end of my presentation now, and I want to leave a couple of minutes for questions, I just want to signpost you towards some useful resources that can help you to learn a bit more about open hardware. So I've talked a little bit about opensource.com, which I've referenced a couple of times in this talk, and I recommend you have a look at that. The Open Hardware Repository is a place on the web where you can find open hardware designs. Some of that might be a bit complicated if you're a beginner, but if you're looking to do more advanced open hardware work, then that could be a place for you. And there are lots of open hardware repositories out there that you can find just by doing a quick Google. And then if you're a beginner, if you want to start as a hobbyist open hardware person, then this link to the Instructables website provides you with a kind of a list of really good open source hardware gifts that you might purchase for either yourself or a loved one, maybe for Christmas. And you can start getting involved in really kind of beginner level open hardware projects. I haven't picked up a soldering iron since I was about 15 at secondary school, but I'm tempted. Now we're going into a second national lockdown here in the UK. Maybe now is the time that I get interested in open hardware and start building things myself. We'll see. But with that, I'm going to kind of wrap things up now and ask if anybody has any questions. I can't guarantee that I'll know the answer to them, but if I don't know, then we can at least try and work it out together. Thank you.
Thank you, Steve. That was a lovely presentation. It was very interesting. Yeah, so as I've said to the others, there's a little bit of a delay when you ask if anyone's got any questions and they actually come through. But yeah, I mean, it's interesting you mentioned the bionic leg project, because actually if I'd filled in your survey, I think I would have made a guess that the projects that I've heard of where people have used 3D printers print amputee replacement limbs in, say, economically deprived countries and also in the United States because of their healthcare system. I won't dwell on the politics of that. Those
Especially
are the
today, yeah.
Yeah, maybe not, but those are the two examples that I can think of. And I guess they're using something kind of produced. The schematics are produced by, say, I can't remember, did you say it was MIT or?
University of Michigan. I think
Michigan,
it was.
right. And they're using those kind of schematics, but then they are doing a kind of charitable act, I guess, by printing them and then making the actual object available. Is that?
Yeah, that's right. Yeah, and there's a similar project at the University of Cambridge around ventilators for kind of more economically deprived countries, and how the kind of open schematics for those ventilators provided a lot of leeway around, replacing different kind of parts of the machinery for things that are more commonly found, and it was kind of allowing people to use whatever they had around to build these ventilators. It's all about kind of making that accessible as well.
Yeah, sure. I mean, I think, like I said in my presentation, that the history of open science and the history of the internet are interwoven. I imagine open hardware has been accelerated by things like 3D printing, and also, even though it's an environmental problem, the cheaply available materials such as plastics.
Oh, definitely, yeah.
You know, if you're making everything from expensive, I don't know, tin or something, then it's not so realistic to have open hardware.
Exactly. And also as well with open hardware, unlike with maybe some of the other open science things that we've been talking about through the Open Science Cafe today, there's a much more of a barrier to entry in terms of actually getting involved in these projects, because, you know, you can make the designs and the schematics openly available, but you can't pay for somebody to have all the equipment and tools that they need to do all of this work. So it's slightly more complicated, I think.
Yeah. And Nathan's just put on the chat that he'd like to work on an open hardware project at some point after the plague. So we have another networking connection, which is lovely to see.
And Nathan works at the University of Manchester as well. So
exactly, yeah, you're both there. And it makes me think, because he's a citizen science chap, and I think you know, this has a lot of citizen science application as well, right?
Definitely, yeah.
It makes me think of the DIY biolabs where people can, you know, turn flies to smell of bananas or whatever, you know, but you could do it on more practical level. Well, not practical, you know, more physical level.
Yes, yeah.
So maybe you guys should set that up. You and Nick,
Nick
at Manchester, the Open Hardware Lab or something.
Yeah, 2021 Manchester Open Hardware Lab.
Yeah, I want to be at the opening. So.
Hello. My name's Jonathan Hankins, and today I'm going to talk to you about open source. As you can see, I couldn't get to Berlin because I've got a problem with the car, but neither could any of the others anyway, so it's no problem. I'm well prepared. As you can see, I've got cardboard and a Sharpie. I'm going to talk about how I'm going to get the car repaired, or how I'm going to repair the car myself, following an open source path. So when I get home, I'm going to have a look on the Skoda forum, because it's a Skoda, and you know, Skoda owners love their cars, and so there's a Skoda forum full of all of this free information about what you need to do to modify your car, or to fix the car if it breaks down. So what I'd like you to do is send your questions in. The boss is looking after that, so keep her busy. Questions about open source, not about Skodas though. So what do they mean by open source? So within the broader picture of open science, we can see open source as part of an open process. We can also think of it though in relation to fixing the car, you know, it's open knowledge, really. It's open knowledge. So it's often used for software or operating systems or research tools or databases. So what do we mean then by open source? So firstly, source. When we're talking about computers, for source, it refers to the source code. And that's the machinery that makes the computer run, the ones and the zeros, I think, I presume, and it's the machinery. And open means that you can get access to it, so you can not only can you see it or read it and use it, but you can also modify it, and then you can let other people, or other people can use your modifications. So the thing about the fact that it's open and modifiable means that you can use it as you will. You know, it's not that you have to buy a package of something and then try and adapt it to your own, or try and adapt your own process to the package. You can actually adapt the program to your needs. So. And we all use it, you know, we don't all know this, but we all use things that are open source. So for example, Android, that many of us have on our telephones, the poorer ones, that's open source. And WordPress is open source that we use for blogging, and Linux for computers, which is what I'm going to talk about, but also cars. You know, this car has a Linux system inside it, and various networking systems. So I'm going to go to the Skoda forum in a minute, but I'm going to use this computer that I've got. I can't show it to you. It's here because obviously I'm using it for the camera. But it's an old computer. I bought it about 8 or 9 years ago. It was €200. It's a cheap computer, and it was great at first. I mean, it looked great. Came out of the box, looked fantastic. It's got one of these, or it had one of these typical, you know, American large, world-renowned operating systems on it that they all come with. And after a few months, it started to slow down like they all do, underpowered computers. After about a year, I couldn't even use it anymore. So I had a look around, started to look around for open source systems, an open source operating system. People told me that you can put them on your old computer. So anyway, I came across something called Lubuntu. It's a Linux distribution. We mentioned Linux before for computers. So it's a Linux open source. Well, it's a lightweight. That's what it is. It's called Lubuntu, and L means lightweight. And Ubuntu is heavyweight, and Lubuntu is lightweight. It's a lightweight Linux distribution, and it's really designed for people like me with old computers that can't use them anymore, with all of this system that's you know, all singing and all dancing and very heavy and requires you to buy a new computer every 5 years. So it's got a good you know, it's there for a good reason. It's designed and developed to help people like me not have to throw my computer away. Anyway, so I installed this open source operating system called Lubuntu. It's a skeleton system, so it just runs the computer, and then what you do is you can add all kinds of different things to it. So it's a lightweight framework, and then you choose the programs. So if you like me, so you write a lot, so you need something that looks like Office or Word, you can get something called an Office suite from another open source developer. So one of the most famous ones is called Apache. An Apache Office suite, it's just like the other one, the big American one, and it's compatible with everything. And this is the big thing about open source, right? All of the stuff that is produced open source, they're like a big gang, these open source crew, and they're making everything compatible. So you can put Apache with Ubuntu or with any of the others. You can also, I mean, we're using Zoom, but there's an open source version of something that could be like Zoom called Jitsi, an alternative. So we could be using that. So it's all standardized so that you can fit it all and mix and match to what you require, which gives you obviously flexibility. So your operating system will go, which is developed by one group, will fit with your Word system, which was developed by another group, and your search engine, Firefox, which is Mozilla, that will also fit in it. And you can build yourself an ad hoc but self-designed beautiful system. And one thing that I should add, because I've done all this, is it was free. It didn't cost me anything. So, and this is typical with open source. Not all open source is free, but you know, a lot of it is. And typically, as is the case with Mozilla, the developers are all over the place. They're geographically distributed. Lots of individuals from all over the place. And because the users can also adapt it and change the code, it's constantly being updated by the users, not only the developers. So this brings all kinds of advantages, right? So it's independent from single businesses. So there's not one person that can suddenly decide to stop it or to update it or to change it. It's a group. It's a group of people. And all of these people have got different approaches. They've got different ideas about why they're doing this. They've got a wide range of technical abilities and capabilities and ideas and aims and philosophies. All of this information, because they're distributed across the world, has to be shared. And so it has to be openly shared so that everybody can access it. And that just by nature makes it a transparent process. Everything's shared, you can see everything. So these are some of the advantages of it. It's adaptable. I mentioned standardization before, and that's really fundamental with open source, but we'll come back to that later. It's innovative, it's in constant development, it's low cost, much of it's free. People dedicate their free time to this. It's secure as well. The people who are developing this are using it themselves. And so there's a lot of peer scrutiny to everything that goes on. And so they're sharing the problems, they're sharing the solutions, and they're sharing them because they themselves use this stuff. It's not profit driven. Mozilla, who do Firefox, don't collect any search information or sell your data because they don't need to make, or they don't want to make, enormous amounts of profit. They're all the advantages. I'm not going to say that there aren't any disadvantages, because there are some disadvantages. It doesn't always work perfectly smoothly, but there are loads of advantages. And when it doesn't work smoothly, there's a forum. And so you write your question into the forum, and all of these people, they're just like the Skoda owners. They love their open source software that they've been working on and developing. And so they will help you to modify it, to get it to work as you want. Just really very similar to the Skoda idea. Skoda are the Skoda forums more about experience. And this is also about technical ability, but it's a sharing of knowledge. So my interpretation of open source is that it's not just about source code or technique or technology. It's about the knowledge and the ability to use the knowledge freely and openly. So it's also well used in many other fields, right? So we've got science, so open science. So here is, I hope you've got a pen. Here is openplant.org. And openplant.org, this is an initiative that promotes interdisciplinary exchange. Okay, so it's a synthetic biology. It's about synthetic biology. It promotes interdisciplinary exchange, open technologies, and responsible innovation for the improvement of sustainable agriculture and conservation. So responsible in terms of that it has what people would think of as a socially advantageous goal, right? So it's aiming to improve the state of the world as its aim. And this is really, this occurs throughout open source. They're doing something with an aim to make things better in some way. So back to openplant.org. The initiative promotes, what they are doing. The initiative is developing new tools and methods for plant synthetic biology. So they want to develop tools that can be shared and approaches that can be shared, standardized tools and standardized approaches that can be shared across the world, and so that all of the work can be shared. So this brings us back to the standardization. They want to provide mechanisms for the open sharing, because you need some infrastructure. You can standardize all your resources, but you need a methodology to share it. So they want to apply these tools and all of these methods to world-leading projects in trait development. So in the development of particular traits in plants. They're facilitating interdisciplinary exchange. They want all types of different scientists and all kinds of people, and not just people who are interested and involved in the process, but as broad a range of society as possible, following a responsible innovation path. So they do a lot of outreach, and they're doing international development. It's an interesting project. I've got another one for you though. This is the next place I'd like to go to. This is iGEM. iGEM is really interesting because they kind of play more with the idea of developing all of this open source. They're doing open source techniques and open source standardized plant parts and molecular biology techniques. So iGEM has 20,000 standardized genetic parts. And they've got standardized tools, a toolkit that you can use for doing your synthetic biology with their standardized parts. And because these parts are standardized and the tools are standardized, they can be used across the globe, like very much like the plant thing. And so what they do is they run a competition. So they run a competition, a synthetic biology competition. It's for undergraduate teams and teams from secondary schools. So they've got enough stuff there and enough machinery and capability and tools to let people who are really beginning in synthetic biology have a go and try and resolve some of the problems that they give them. So they give them a problem or a series of problems, a standardized toolkit, standardized parts, and they try and the competition is to try and resolve these problems. Then they have a final. It's in Boston, Massachusetts. It was anyway in the good old days, and they give a prize. It's really a very similar aim, just a different way of going about it to Open Plant. They're interested in a common syntax for exchanging DNA parts for plants, for example, as well as common research tools and open and shared digital tools. Because once you've got this far, so we have to picture all of this stuff that we've been talking about today as a long process. It's a science process. And in order to get towards the end, you need some shared digital tools as well. So all of these things that I'm sure you've been watching all afternoon, like me, they all can be seen together as all part of a process. So we might think of it, you know, they're here with the back to the car's still sitting here. We might find more lab coats, fewer overalls, a lot less WD-40, but comparable systems with similar structures and goals from synthetic biology, but openness, open access to being able to do it, really, as is as are the people at the Skoda, in the Skoda group. It's access to being able to do it. Databases are a big open source area, offering open source access to open data and publications. But that's something that's going to come along in the next talk. So I won't go too much into that. The EU is promoting open science and open source projects. It's a fundamental issue in its funding. So why is this? Why would they be investing 500 billion euros or however much it is in open source and open science? And the reason is it looks advantageous to science. If you think about some of the big projects that have gone through open source and through open science that have been successful over recent years, you know, it does seem to demonstrate that putting 2 million heads every day together to develop Ubuntu brings its advantages. I'd like to thank all at Berlin Science Week for letting me do my presentation. Thanks to everybody at ORION. So ORION is a European funded project. They've got a MOOC on open science that's really very interesting, well organized. I've followed it, it's good. They do a train the trainer course. So if you want to step up another level, you can do a train the trainer course, which sets you up to train people into open science. At the end of the train the trainer course that I've just completed, the last thing that we do is to do this presentation in Berlin. So this is the end of the course. I can thoroughly recommend it. It was a fine course and the MOOC, and it's all free. For more about me, if you want to know any more about me, you can type these 2 words into Firefox and you will find me. That's J Hankins, or just Hankins, that's my name, and Bassetti, that's where I work. Keep the questions coming, and I have a disclaimer because there really is nothing wrong with the car. Thank you.
Thank you, Johnny. That was a fabulous presentation and very unique and original. But it's true about the car, though, right? You told us. You really did fix your Skoda through an open source forum.
You do. That's what they're doing. It's an open source to experience and to information. And the problem with the Skoda is that the parts aren't interchangeable. So the system falls down a little bit, because then you have to go and find yourself, the correct parts. So it's not an entire chain. It's a working practice to try and resolve some of the problems, because it's not an open source machine.
Well, if you had the schematics for the parts, a la what Steve was telling us in open hardware, they have a bigger chain, right?
Yeah. Yes, if anybody publishes all the necessary information to replace anything that you need to replace, you can build it yourself. I mean, that's what people were doing in the old days.
In the old days, yeah. I mean, I think it's really interesting that you were saying about, the computer, and I think we hear about open source as something that's quite, maybe sort of quite techie. But this sounds like something that has some very real world applicability, something that everybody might be wanting to do.
If you do go down the open source with, for example, with your computer, there are a few problems with that. It's not totally glitch free, because some of the producers of things that you can't get open source don't make them compatible. You have to kind of find solutions, but that's part of it, is the fact that you can find solutions. You end up not being able to modify the thing that you've bought, but trying to modify the system, the open source system, in order to make the thing that you've bought work. I find that people who work in open source, they really have a philosophy. There is a philosophy behind what they do, and it sits within responsible innovation. If you think about, so René von Schomburg, he's a big name in responsible innovation, and he's had a lot of effect on what the European Union and the European Commission of how they've interpreted responsible innovation. And one of the main points is that their main ideas is that their innovation should work towards a goal that is advantageous to the most people possible. So they see it within the European Union, but really you could see it for the greater good of society. So an innovation that works for the greater good of society, rather than an innovation that works for any other reason, really. And if you think about my example of the Lubuntu, it's been developed by somebody specifically to help resolve this problem of computers becoming obsolete and having to be replaced in 5 years. I mean, that is no good. That is no good for anybody. It's not good for the environment. It's not good for the pocket. It's only good for computer manufacturers.
Right. Yeah, exactly. And it's incredibly frustrating as well. And as you say, I mean, it just ends up in landfill and leaking into the sea and what have you. So, I think that's an interesting point in terms of open source and sustainability are often one and the same. So, I think that's something that both camps should talk to each other maybe a bit more about.
You find a lot of the computers in cars, though, are running open source systems.
Oh, okay. Yeah, it seems to be the more the big computers, the sort of the machinery computers are a bit more.
Well, it's much more widespread in the world of business.
Right.
Making things operational for precisely your needs. So rather than having to buy something pre-packaged, being able to build it up, you can make you could have an agreement with a group of open source people that will adapt your package for you.
And I mean, obviously in science, and I mean, you said you've been here all afternoon, so you saw the work that Inga's doing, which is again kind of taking this idea of, okay, these are what the big companies are doing, but how can we make it something that ordinary people can have some power over, some control over?
Yeah.
Yeah.
There is a trend, you know, in open source. There's a bigger debate, and you know, like you've just had in, we've just had in practically all of the things about how open can you make it. And here, if we're talking about, you know, the big M producing all of this computer technology, you know, how open are they? Do they want to be? To some extent, it seems like a bit like a battle, and I think that a lot of people that are doing this open science, open source production, see it as a battle. Yes. There's one thing that I forgot to mention as well while I was rambling on about the car. With an open source running system on your computer, there are so few less bugs and viruses, because a lot of the viruses are aimed at attacking the Microsoft, you know, we have to say. They're aimed at attacking Microsoft because people don't like the way they go about their business, or because, you know, they want to undermine them in some way. And you do not find that. I don't want to say that there aren't any viruses, because there are some viruses, but it's an incomparably small amount.
Yeah. Yeah.
It's seen as a force for good, and so people, the technical people that know how to go about building a virus, they don't build a virus to put it on their mates' computers.
Right. Yeah. Yeah, that makes sense.
So they really, you know, you don't need any antivirus.
Well, there's another saving in that.
Yeah.
In that as well.
And that at the end of the day, that's what makes the computer so slow. That's why I had to stop using it in the first place.
Right. Yeah, that makes sense.
It's all the antivirus stuff.
Yeah. Well, I mean, I wasn't expecting to learn so much about how to make my computer run better, to be honest, but I'm happy to. We said to use real life examples, and you've taken it to the logical conclusion, I think.
I've got to admit though, you know, I'm stood outside the house. I've got all of these lights here. Yeah. Stood outside the house with floodlights.
That's only you would have thought to do that. That's wonderful. I'd love to talk about open source longer, but we have to move on to the.
You do. Thank you very much. It's been a joy, and I'll see you on Monday.
Indeed. Yes. All right. Take care.
Thanks, and you.
Okay, everyone. So the next presentation is coming up in 5 minutes, but it's me essentially. So it's going to be me giving the next talk on open access in 5 minutes time. I'm going to share my screen, but I'm just going to put on the slides for the next talk that I'm going to give. Rather than, no, that's not what I wanted to do. Okay, so Zoom is being difficult now, as usual. And yes, here we go. So I'm going to start the next talk on open access in a few moments. This is the MOOC, by the way, that Jonathan so kindly said was good and worthwhile. I put a link to it in the live chat, so please do check that out. Yeah, a couple of minutes and we will start talking about open access. Right, I can hear the church bells chiming for 6 o'clock. So I think that means it's time for me to start my presentation on open access. So this was a little bit of a last minute effort, I have to confess. Unfortunately, a couple of our graduates were unable to attend because of illness. We are in the middle of a pandemic, so I guess that's kind of to be expected. But I have talked about open access many, many times. So I'm gonna talk again about it today, and I'm always happy to. I think it's very important. Hopefully we'll have some time for questions at the end, and we'll have some exchange of ideas. Okay, so open access. So I want to start by telling you a story. This is Anna. And Anna studies biology at school and then at university. And she ends up doing her PhD in biology, in, let's say, molecular biology. Maybe she gets her PhD at the Max Delbruck Center for Molecular Medicine. But she decides that she doesn't want to do a postdoc and become a scientist. She decides that she wants to go and work for an NGO, a company or a non-profit company. So she decides to go and work for an NGO like that. And a little while later, she meets Peter. And as is the way of things, Anna and Peter fall in love and they decide they're going to get married. So they get married and they're very happy together. But then Peter gets sick, really, really sick, really ill. And it's one of those awful rare diseases that nobody really understands. And the doctors and the consultants are telling Anna and Peter different things. And they're saying, well, we could try this and we could try this, but it's all very new and it's all very in early stages. And Anna is, you know, she wants to do what she can to help her husband. And she thinks, I have a PhD in molecular biology. I'm a biologist. I understand how the body works. I understand how cells work. Surely I must be able to understand this stuff and make some kind of informed decisions about these issues. So she's sitting in the hospital and she tries to read some articles about these diseases, about how it affects the body on a cellular level, but she can't. She's not affiliated with any university anymore. She works for this NGO, and she can't. She has no ability to do that because these articles are behind a paywall. So she just buys them, and they cost 50, 60, 100 euros per time. She ends up spending nearly 1,000 euros just to read some articles, many of which aren't actually that helpful for what she wants. And the thing is, Peter and Anna have paid taxes all their life. They paid for the research that is being discussed in these publications, but now when they need them, they can't access them. And that essentially is what open access is. Open access is the initiative and the belief, the ideological belief and the practical implementation of that belief that everyone should have access to research publications without cost. So that's the fundamental baseline for open access. And there are other aspects as well, like for instance, countries that aren't as rich as say, you know, Western Europe or the US, they won't be able to afford the subscriptions for journals. They won't be able to access these journals in the same way. And that then holds back their researchers from making progress. So it's not just about individuals accessing publications, but also about entire nations. So let's take a step back. Why? Okay, so open access sounds like a great idea. So why isn't it being done? Well, the problem is what we might call publish or perish. So in academia, there is a shortage of funding and there's a shortage of full-time tenured positions compared to the amount of people applying for those things. So you have to have some criteria for how to award that funding and how to award those jobs. And the criteria that has been kind of collectively agreed upon, or at least certainly until a few years ago, was high impact journals. And we'll come on to high impact journals in a second. And the number of citations you have, the number of times you publish in high impact journals. So the way that research and researchers are awarded is by publishing in the highest impact journal and publishing there the most amount of times. Now, high impact journals are run by publishers. I'm sure you've heard of them: Elsevier, Springer Nature, Wiley, these ones. And they make a lot, and I can't even begin to stress how much a lot is. You can look it up for yourself. A lot of money, huge percentages on the not only the subscriptions, so the libraries pay a subscription to have these journals available for their own researchers in-house. So each university pays a subscription, each individual university, but then also paywalls from individuals like Anna in the story. And then we come on to the impact factors. You think, okay, well, maybe that's the price we have to pay for having an impact factor. Well, unfortunately not, because the true nature of impact factor is a lie. I feel like I'm telling Keanu Reeves about the Matrix, but yeah, it's completely manipulated. Journals basically, and publishing houses basically negotiate what counts as a publication, and they swap in and out these things according to what will look best for them. So one year they might count in editorials and one year they won't, that kind of idea. And so the impact factor is falsely manipulated. So it's not even a true reflection of the worth of a journal. Years ago it was, there was a reason behind it, but now it's become a false kind of make-believe number. So we haven't even we're not even paying for something that's real. We're paying for something that's manipulated by the people we're paying, which when you think about it as a sort of monopoly case, you know, like the one they brought about, Johnny mentioned Microsoft, Bill Gates was brought to court for, you know, monopolizing. That's, you know, that's very, very kind of walking the line with something quite similar. So that's not good. So, okay, so hopefully I've convinced you now that we probably should go for the open access. So what are the options? So the first option is green. So this is where you publish as normal. So the article goes to the publisher, but then the author places it in a repository, either an institutional one, i.e. like something that the library runs, or a multidisciplinary one, for instance, Zenodo or what have you. But there's often an embargo period. So this can be 3 months, 6 months, even 24 months in some extreme cases. And that means that article, that version of the full text article isn't available until after that time period. And in that time period, it's still behind a paywall. So it's the free version. It's the truest form of open access, but unfortunately there is still this issue of embargoes. Then there's gold open access, which is instant. In the moment the paper is published in a journal, it is available, but unfortunately there are what's called article processing charges, APCs. Now this varies by discipline. In some disciplines you have to pay to publish anyway. In some disciplines you wouldn't do that, so this is an additional amount. And this is one of the problems that initiatives like Plan S, which I'm going to talk about shortly, have come into, because in the humanities, for instance, we don't expect to pay to publish, but in some of the sciences you do. So, but the APCs are around between 2,000 and 3,000 euros, depending again on discipline and on the journal. But this, of course, is more money that is going towards journals. So some people are resistant to gold open access for that reason. There is another aspect to green open access that I'll just flag, which is preprint. I'm sure during the pandemic, you've heard about preprints. This is the version of the article before peer review. So it's the last draft manuscript before you send it for peer review. And this can go on things like archive, which I mentioned in my previous talk. It's the physics have been doing this since 1991. BioArchive for the for life sciences is becoming increasingly popular. And the advantage of this is more between scientists. So you can see a paper very early on because obviously the publishing process is very slow. Peer review is very slow. It can go back and forth. And a lot of funders now accept preprints in an application, and so you can say, well, I have worked on this. This is what I found out. Even if you waited for the journal to publish the post print, you might miss the deadline for the funding. So as a researcher, that's really good. As an ordinary member of the public, you can of course go to preprint archives. But there is the proviso, it hasn't been through peer review. So that is obviously the downside of that. Each of these have an advantage and a downside, and that's the one there. I mentioned Plan S, and Plan S is an initiative by Coalition S, which is basically a group of funders and universities across Europe who are trying to basically force the issue of open access and make it essentially mandatory. So if you receive funding from these institutions and funders, you have to publish open access. And that's kind of coming into effect kind of around now, really. And there's been a lot of discussions and back and forth on this. And I'm sure, if someone in the comments has an update on Plan S of what the current status is, I'd be really interested to hear that, because we did, as I mentioned in the previous talk, we ran a podcast and we did an interview about Plan S, which was really interesting, but I'd like to know what the most up-to-date status of things are. And then also something you might have heard associated with open access is DEAL. And that's something that kind of emerged from the German universities, but has sort of spread to a number of other countries. And that's with Springer Nature and Wiley, I believe, where these subscription costs are sort of consolidated on a national level, and open access is kind of what's the word? Almost like a right for every researcher. Again, there's loads of information. I haven't unfortunately got time to talk about them all here, but if you just Google Plan S or DEAL, you'll find, and also happy to answer questions about them. But I just wanted to flag those as some top-down initiatives that are really making open access kind of the norm, the new normal, as a phrase that we're all so familiar with the last 8 months, the new normal. And this I just wanted to talk about, actually very nicely. I've segued into my own slide, the new normal, so COVID-19 and open access. So on the Coalition S website, I found this quote, which I think is very interesting. Embargoes are lifted, paywalls abolished, and preprint servers like medRxiv and bioRxiv have accelerated research evaluation and discussion. By opening up research in times of crisis, subscription publishers have implicitly admitted that their paywalls and embargoes were unjustified and insufficient to start with. And this is an argument that's being made by a lot of people, that essentially when the COVID-19 became this crisis, and obviously we're all, all the scientists are working for a vaccine and wanting to, share discoveries as quickly as possible, a lot of the publishers lifted their paywalls, and preprint servers really kind of came into their own. But of course, by doing this, the publishers, as Johan here basically says, the publishers then admitted that you can do science faster without paywalls. And he goes on to say, and I'd really recommend looking it up. I'm sure if you just Google COVID-19 open access, Johan, or Coalition S, you'll find it. But he goes on to say in some depth about this shouldn't be a temporary measure. we shouldn't go backwards now. We've made this new normal. It should be the normal going forward. And I think that's a really important point. One other thing I just wanted to talk about is the rapid reviews COVID-19. So again, to mention the podcast, we did a podcast interview with the one of the main editors of this, and this is something produced by MIT Press. Basically, it's a very innovative way of looking through everything that's being published on COVID-19 and sharing it as quickly as possible, but with peer review, which is kind of protecting it from sharing things that aren't necessarily fully verified. And they're actually using some form of AI peer review, and also utilizing PhD and postdocs to be able to human check the AI. So they've got a really interesting system, and I really recommend, I'll share the link in the comments in a moment, but I really recommend you listen to that episode, because it gives a great insight into the possibilities going forward that COVID-19 have opened up in terms of open access. So I will stop there. That's my attributions. As we learned earlier on open content, attributions are important.
Okay, so good evening. My name is Luis Mayor, and this team is going to show you a brief presentation course on science communication. The team is composed by me, Luis Mayor. I am project manager in the Iseki Food Association. Josiline Chigwada, she is librarian in the Bindura University of Science Education. And Janis Kreicbergs, he is project manager in the National Library of Latvia. In this course, you will learn what is science communication and its benefits, how to conduct effective science communication, and you will learn about science communication channels and tools. Before entering into detail on what is science communication, we would like to show you some funny examples of good or bad, you decide, science communication in the Big Bang Theory series. Okay, so this is the first example.
Introduction to physics. What is physics? Physics comes from the ancient Greek word physika. It's at this point that you'll want to start taking notes. Physika means the science of natural things, and it is there in ancient Greece that our story begins.
Ancient Greece?
Hush, if you have questions, raise your hand. It's a warm summer evening, circa 600 BC. You've finished your shopping at the local market, or agora. And you look up at the night sky, and there, you notice some of the stars seem to move, so you name them Planetes, or Wanderer. Yes, Penny?
Does this have anything to do with Leonard's work?
This is the beginning of a 2,600-year journey we're going to take together from the ancient Greeks through Isaac Newton to Niels Bohr to Erwin Schrödinger to the Dutch researchers that Leonard is currently ripping off.
2,600 years?
Give or take. As I was saying, it's a warm summer evening in ancient Greece. Yes, Penny?
I used to go to the bathroom.
Can't you hold it?
Not for 2,600 years.
And then other example.
Introduction to physics.
Pardon. Yeah. A short example.
We're going to show you girls how cool a job in science can be. How cool, you ask? Well, how about negative 273 degrees? Because that's the temperature at which entropy reaches its minimum value. Did I just learn something new and have fun doing it? What? All right. So now let's bring out theoretical physicist, Dr. Sheldon Cooper.
female children. Allow me to inspire you with a story about a great female scientist. Polish-born, French-educated, Madame Curie. Co-discoverer of radioactivity, she was a hero of science until her hair fell out, her vomit and stool became filled with blood, and she was poisoned to death by her own discovery. With a little hard work, I see no reason why that can't happen to any of you.
So we suppose that you understand that it's not a good way of communicating science. We would like to do an activity with you. Okay, we would like to do a Mentimeter. You have to go to www.menti.com, enter this code, and answer to the question: have you experienced such science communication trauma? Okay. So we will leave 1 or 2 minutes for you to participate, okay? And I'm going to show in the screen the results of this question.
I put the code in the chat. Ah, yeah, there we go.
Yeah.
There we go.
We have some inputs. Let's wait a little bit. Yes, as a student. Yes, as a lecturer. No to people. So, other examples about the consequences of bad science communication. For example, this image about the 4 COVID personality types. Okay, the one who believes in science, the one who denies it, other doesn't understand, and other believes in magic. The flat earth theory followers, and those who are feared about the 5G technology. So this is a consequence of bad communication. So what we have to do to do good science communication? Let's start by explaining what is science communication. Science communication is the practice of informing, sharing wonderment, and raising awareness of science-related topics. As a prestigious British scientist said, science isn't finished until it's communicated. We can identify 2 main types of science communication: science outreach, typically conducted by professional scientists to non-expert audiences. Okay, as examples here, David Attenborough in biology, Jacques Cousteau in marine science, and Carl Sagan in astronomy and general science. But do you think you need to be a prestigious scientist to do science outreach? You will find the answer perhaps in the following slides. The other type of science communication is science enrich, where expert-to-expert communication from similar or different scientific backgrounds is done. Okay. As examples, scientific journals, or conference events with oral presentations and showing posters, okay? So these are the 2 main types of science communication. But why are we interested in communicating science? Communicating science have different benefits. At personal level, enriched scientific communication is part of the normal scientific work, allows researchers to promote in their careers, gain visibility in your scientific area, putting ground for future scientific collaborations and projects, meet people from other institutions and sectors that might offer you other career opportunities, and also, of course, the personal satisfaction to show others your work. And a more general, and in a general way for science and society, support for scientific research, increase the public understanding of science, very important in these moments, for example, versus science denialism, climate change, COVID negationists, terraplanists, creationists, and other ists that you know, informed decision-making, including political and ethical thinking, motivate future generations to pursue a scientific career, and in general connect scientists to society. Okay, and related to this last point, I would like to show you this image is related to an event where Albert Einstein and Charlie Chaplin met. Okay, and when they met, Einstein said, "What I most admire about your art is your universality. You don't say a word, yet the world understands you." Okay, and Charlie Chaplin replied, "It's true, but your fame is even greater. The world admires you when nobody understands what you say." So we can see here that Einstein was not prepared to communicate science, and perhaps society was not prepared to receive the science from Albert Einstein. Okay, so how do we do effective science communication? And now I let my colleague Janis to follow with the presentations.
Okay, thank you, Luis, and good evening, ladies and gentlemen. As I was presented, my name is Janis Kreicbergs, but today I will start with the material of our teammate Josiline prepared on how to do effective science communication. Okay, next please slide. So we have seen in previous video how important for effective communication is to know your audience, and taking that in mind, build your message you want to tell. If Sheldon will take in mind our lecture, I'm sure next time when he will give lecture for so-called female children, he could get a better connection with audience. And actually, I have very similar trauma too when giving lectures for young girls. So, but also from some advices is using metaphors and analogies to tell your story and avoiding jargon. Okay, next slide. Luis has already shown in the picture with Albert Einstein. Can we switch to next?
Can I pass the slide?
Yes. Next slide, please. So Luis has already showed a picture with Albert Einstein and Charlie Chaplin, that the key lies in making your science understandable for audience. And you have to learn to communicate and know which channels to use and how to mix them. And actually, this is the story of next slide, which is my part of presentation. So we can switch to next. About science communication tools and channels. So let's go further. And if we talk about communication channels and tools, we can divide it in two directions, inwards direction and outwards science. The inward direction can be called science to science or science to scientists. And there are tools and channels known for scientists for decades and even hundreds of years. For example, books, journals, manuscripts, reports, and also conferences and proceedings. And I also see how summer schools and workshops are getting quite popular lately. So these are so-called, I call traditional channels, but we can move further to additional maybe or online communication channels. Yeah, we can switch to the next slide. So these are online channels for science to science, and here we see a rich variety of additional tools. These are academic networks and professional networks. I hope and I guess a lot of us know these, and we have our profiles here. We also see that the repositories are not just a place we store our research results, but these are also very good channel to spread our knowledge, and there are a lot of discovery services work here. And also I would like to mention platforms for finding research partners, finding funding, and building networks. So And if we move to next slide, we can talk about science to society, or so-called outward direction, which helps to make our efforts understandable for general society and to show for society where the tax money goes in understandable language. So also here we can mention newspapers, magazines, TV, radio programs, but with prefix popular, popular science magazines and research results magazines. Also here we see exhibitions, museums, different centers for children to understand the science in their language, crowdsourcing, collaborative projects, contexts, workshops, the rich variety. But if we move to next slide, we also, of course, have online tools. We all know, and most of us live in social networks, so we know them. YouTube channels, podcasts, blogs, wikis. And if we talk about children, we can see how it's popular to use virtual reality tools and objects to engage children in understanding science. So if we move to last slide, I can say it was very, very short sprint through this communication topic. And I want to thank you for your attention. And here you will find our emails. So thank you for watching.
Thank you both. Yes, I mean, I certainly think that you covered everything in terms of what different ways we can communicate science, and it really highlights the possibilities of ways we can communicate science. And of course, I love the videos at the beginning. I knew you were going to use them, but I still think they're excellent examples of bad science communication. There's a little bit of a delay, so I'll just see if there's any questions coming through. But while we're just waiting for that, I just wanted to raise with you that, so the thing with Sheldon is that he's in love with his own cleverness. That's why he can't connect with Penny. He's too in love with how clever he is as a physicist. And I think what's really nice is that I think what's his name, Fauci in the US recently came and said that this wasn't one of the three things you should do for science communication, and the third one was it's not about being smart, it's about making sure everyone understands you. So I think you really made that point really clearly with those videos. So that was very cool.
Yeah, thanks. We tried to cover all topics. Perhaps you should have focused in just one, but
no, it's an overview, right? Yeah.
An overview, yeah. It's an overview.
Yeah. I just want to add, you also have to not to be very smart, but also you have to be very flexible, because from my experience, if you teach one subject, you have to be very flexible to your audience. You may teach one thing, but it's necessary to tell it in different ways for different people.
Yeah, exactly.
Yeah. And engage people and explaining things in the same level of the people. This is the way how you engage people in the society to the science. I mean, as Emma said, if you think you are in a higher level and you don't go down to the level of the others in your mind, okay, it's not possible to connect people.
Yeah, absolutely. I mean, exactly. You need to think about what your audience is thinking about, and really think about that perspective on things. Okay, I think there may well be some questions on the chat, but I think that's time for now, and I'm sure people want to think about what you've said, and I'm sure they'll contact you directly and perhaps on the live chat. So if you both kind of go over to the YouTube, sometimes there's some questions a few minutes after the presentation is actually finished, so that's always nice, and you can answer them there. So I want to thank you both for giving such a wonderful presentation, and such an interactive presentation, and such a funny presentation. So thank you both for your hard work, and of course to Josiline. Josiline, who couldn't have unfortunately join because of the connection issues. But thank you both.
Thank you.
Okay.
Thank you very much. Okay, so all that remains is for me to thank everyone who has attended today. Some of you are still here, our loyal fan base, and some of you have joined later and have maybe just turned up for science communication, in which case I hope you enjoyed the last talk. I certainly did. This will be recorded. This presentations will be recorded, and they will be made available openly, of course, on Zenodo. As Johnny said, we have a MOOC, which will kind of take you through open science in six modules. And we also will be doing probably a future Train the Trainer events. So if you'd like to contribute to that, we'd be more than happy to have you. So once again, thank you so much for joining us today. Obviously, it wouldn't have really worked if there was no one watching. And the most important thing, of course, is to thank each and every one of our speakers who all did a wonderful job. Every presentation was really interesting and original, and I learned things, which is the best kind of way to spend a day, really. Also, thanks to Zoe Ingram, who's been co-moderating with me, and to everyone else who's been helping out these last few weeks. I think you know who you are. Okay, that's it for today. It's more of an open science dinner at this stage, and we wish you a lovely evening and goodbye.